Today, this team of elite engineers is embarking on an epic endeavor.
It's very, very big.
They are attempting to build an extraordinary vessel. One of the biggest and most advanced cruise ships in the world.
It's like a puzzle, it's a bigger puzzle.
You cannot make a mistake.
This is a ship of giant proportions, constructed from 35,000 tons of steel. It will carry more than 5,700 passengers and have a massive central promenade.
Now the pressure is very high.
To build this Leviathan, the team must battle mountains of metal.
We have to solve problem after problem.
And punishing deadlines.
We cannot have delay.
It's time now that the ship works, and works well.
This colossal cruise liner ranks in a league of ambitious new engineering wonders that are bigger, faster, taller, and more advanced than anything ever constructed before. This series charts the inside story of the extraordinary challenge of building these giants. In Saint-Nazaire, France, this team of shipbuilders is starting work constructing the prototype of a new class of giant cruise ship.
This ship will be impressively huge. I mean, the last 15 years, ships, they've grown tremendously. So yes, it will be big.
With its ambitious size and scale, this new prototype will push the boundaries of cruise ship design and engineering. She is called Meraviglia and is the vision of Pier Francesco Vago.
Meraviglia, I think, will really turn heads. We want to make a statement. She's going to be a big ship, and we want to make her fun. We want to have a lot of innovation.
Pier Francesco is investing over £725 million in this ocean liner.
We're talking about a lot of money, so I'm certainly not going to save, on innovation, and I want the latest.
It rests on the shoulders of site manager Gaetano Rolando to make sure that Meraviglia is built to set sail on time.
Oh, this is a very exciting challenge for me and for all our team, because every day is different, every day is something new.
Gaetano has constructed 6 vessels over the past 15 years. But nothing as ambitious as this one.
So this is the biggest ship I have built. I'm very excited for this big challenge.
This is the giant Gaetano and a team of 3,000 shipyard workers must build. Measuring 1,036 feet long and 214 feet tall, this ship will weigh more than 3 times as much as the Titanic. On board, they plan to build 20 bars and restaurants, 2 theatres, and 4 swimming pools. To cater for the 5,700 passengers staying in 2,244 cabins, 4 giant engines will power the ship, propelling 2 rotating 170-ton thrusters. At the heart of the vessel will be a Mediterranean-style shopping promenade, topped with a 262-foot-long LED screen ceiling, the longest screen ever built on a ship. The company has built 12 cruise ships over the last 29 years, but this will be the largest and most advanced liner they have ever attempted.
The pressure is huge, the risk is huge. You keep a ship for 30, 50 years, you can't make a mistake.
To fill the ship with passengers, tickets for the maiden voyage have gone on sale before the vessel is complete, and it's already sold out. Cancelling this high-profile journey would be a disaster, costing the company hundreds of thousands of pounds. So there's no room for delays.
The toughest part of my job is to deliver the vessel on time.
With the clock ticking, Gaetano and the shipyard have just 26 months to build, test, and deliver the massive ship.
Every day, day by day, the pressure on our shoulders coming.
Building such a huge new class of vessel requires a huge shipyard. The STX yard in Saint-Nazaire, located near the deep waters of the Atlantic, makes it the ideal place to build this giant. Marine engineers here have a rich shipbuilding heritage. The prestigious SS Normandy and the Queen Mary II, both the biggest cruise ships of their eras, are just some of the grand historic liners built here.
Only a few shipyards in the world can build a ship so big like Meraviglia.
Constructing this prototype vessel involves a series of key challenges. This is the plan. First task, transform 35,000 tons of steel into 50 huge sections, called mega blocks. These blocks will join together to form the ship's hull. Next, workers must build and attach two special thrusters, called azipods. These carry the vessel's 25-ton propellers that will push it through the water. Once afloat, the team need to construct and furnish the 2,244 cabins, fit out the decks, and install the 1,450 panels to create the promenade's LED ceiling. Once complete, engineers will need to test every aspect of the ship, putting her through her paces in a series of grueling sea trials. Gaetano and the shipyard start with 35,000 tons of bare steel. They must somehow transform it into the 50 giant mega blocks that form the ship's hull.
All the steel plates arrive in this position, and then by the crane will be fitted inside the workshop as they need. It's a very heavy and massive challenge for all of our team.
Workers feed each sheet of steel into these giant machines. They fire an 18,000 degrees Celsius jet of superheated gas called plasma through the steel. This cuts the individual pieces of ship to size with absolute precision.
Cutting all these pieces by hand, of course, will take years. So they use the plasma cutting to be faster.
They build the blocks from around 300,000 individual steel pieces. It's a giant jigsaw. Workers must sort and deliver each piece to the right workstation so it ends up in the correct place. Any mix-ups could delay work on the whole project.
This machine is very accurate and can identify each pieces.
Engineers assemble sections of the ship in these workshops. They piece together giant panels that form each megablock upside down. This makes it easier to install the ship's crucial services into the ceiling. The 932 miles of electrical cable, 124 miles of ventilation ducts, and 158 miles of pipework.
Chez STX, nous fabriquons les panneaux à l'envers pour faciliter la tâche de travail en atelier, quoi. Parce qu'il y a certaines zones qui sont très compliquées. Je vais vous donner mon avis personnel. Pour moi, c'est un superbe bateau. Je ressens un peu d'émotion dans la mesure où j'y ai apporté un peu de moi-même, quoi.
Each completed panel measures one deck high. Once fitted out, workers must place it into a special frame to allow the yard's giant crane to lift and flip the panel over, turning it the right way up. Around 20 panels make up each mega block. The crane lowers each completed block into the dry dock, where workers weld them together. It takes nearly 11 weeks to construct the blocks, but with multiple crews building more than one at a time, this method speeds up the time it takes to build the vessel. This technique is so successful that workers use it to build almost every ship at the yard.
For this panel, almost 100 tons, the weight.
They call in this giant gantry crane to turn each massive panel over and assemble the megablocks. Soaring 213 feet tall and with a lifting capacity of 1,400 tons, this is one of the biggest cranes in Europe. In charge of this aerial ballet is crane operator Loïc Gouan.
Très grande responsabilité. Il faut avoir des mouvements assez calmes quand même. Il ne faut pas envoyer des grands coups, surtout pour la conduite ou sur les chariots.
So the position of the panel on these tools is okay. So everything is aligned and is locking.
Loïc receives the all clear to slowly raise this giant panel.
The wind is also an important factor of this operation. If the wind is much more, they have to stop the operation. Now is most critical because we'll come out of the hinge.
The panel hangs like a huge airborne sail. A sudden gust now could prove disastrous.
It can make a damage the crane to other panel, to the people. Up to now, everything is going well.
They lower this panel down to form the base of a new mega block.
Now is time for lunch. Most important part of the day.
Each mega block takes 11 weeks to build. The blocks fit together to form the ship's bow, central hull, stern, and the captain's bridge. It takes around 11 months for the shipyard to fit all 50 giant mega blocks together to form the vessel's skeleton. With more than 8 miles of joins to weld and 10 football pitches of bare metal to paint, the dock team has their work cut out. As the bare skeleton of the vessel begins to take shape, another team is gearing up to start the monumental task of fitting out the inside of the ship. Giuseppe Maresca is in charge of overseeing the installation of a staggering 2,244 cabins.
It's very important for us to have all the cabins on board in the right time and before the delivery date. Otherwise we will have unhappy guests and unhappy bosses. The cabins will have an access to a balcony. To check the position of the cabin, we can see the tracing on the floor. This is where one cabin will be, and there another one, there another one, there another one.
Giuseppe faces an enormous problem. It would take years to build and fit out each individual cabin on board by hand. The ship would never hit its maiden voyage. They've been developing an ingenious solution to this problem at this special factory just outside the yard.
Welcome to the cabin factory. And this is where we build our cabins. Every 25 minutes we produce one new cabins. That means that in one day we have produced about 16 cabins per day.
Instead of building each cabin from the ground up on board the ship, Patrick's team is pre-assembling each room, just like flat-packed furniture, on this unique assembly line. Each unit starts life with a watertight bathroom shell. They install the electrical wiring, plumbing, bed frame, even a desk.
Meraviglia has been quite a big challenge for us to produce such a large quantity of cabins in a small period of time. We start with a base frame and we put the walls around, and then we will do the roof on the top. We'll put the furniture inside. I've never had a shower in this wet unit, but my production manager, yes, he has already tested that on the production line, yes.
They fit the air conditioning, Wi-Fi points, and touch-sensitive lighting to complete each cabin unit.
Here, most of the furniture comes already assembled, except the big furniture that we will assemble ourselves. Again, one wardrobe every 25 minutes.
Before finishing, they need to install one key piece of equipment to make sure that the cabins fit quickly into place on board.
So here we go. This is where we're going to connect the cabins to the ship with that plug. This is plug and play. The cabin is just finished. We just need to connect the cabins to the ship and it will work. As simple as that now. It would be impossible to produce Meraviglia on time if we would build 100% of the cabin on board, without any doubt.
After a mere 25 minutes, the assembly of this cabin is complete. Next stop, the shipyard. The team must now gear up to float the ship to a different quay before workers can continue installing the vessel's cabins, restaurants and entertainment zones. Before they move the ship, they must first fit its two massive propellers onto the stern. Loïc Morin faces the daunting task of designing the complex propulsion units. They must be capable of propelling this enormous ship without compromising the comfort of the journey.
The propeller design is unique for each cruise ship. The challenge to design a propeller for Meraviglia is to reach this compromise between the propellers, efficiency and the negative effect which can generate noise and vibrations on board the cruise ship.
In 1907, during the sea trials of the British ocean liner the Lusitania, engineers reported intense vibrations running throughout the ship. The cause was traced to the ship's propellers. This is the problem. When a ship's propeller rotates, it creates a vortex of low pressure behind the blades, made from millions of tiny air bubbles. This process is called cavitation. When these bubbles implode, they send out shock waves through the water, hitting the propeller and ship's hull. If enough bubbles implode at once, it can cause vibrations that run through the ship. These can create an uncomfortable ride for the passengers and crew.
The standard of a cruise ship is very high, so we have to be sure that the ship will be quiet and with no vibrations and with no noise levels due to this propeller.
With the stakes high for this giant new class of vessel, no off-the-shelf propeller design will work. So Loïc has had to come up with a bespoke solution to ensure this vessel is their smoothest ship yet. To try and minimize cavitation, he has designed a propeller with 5 blades, perfected their shape, angle, and distance from the hull, and the speed at which they will rotate, to make sure that the ship glides smoothly through the water.
So we are using the most advanced propeller design tools in order to be sure that we are supplying to the ship owner the best propeller design over the world.
Building such intricate propellers is no simple task.
I love my job, for sure. I love to make the best propellers in the world.
Workers cast the propellers from a special molten bronze alloy, a mixture of copper, aluminium, iron and nickel.
The cruise propeller blades are very big blades.
They cast the 25-ton propeller in separate parts, the blades and the central hub. Workers fill a series of boxes with resin-bonded sand to create the molds for the blades.
What we do here is to put sandbox in front of the robot, and then the robot will be able to remove the sand and create the final shape of the mold.
They must pour the molten alloy into the mold without stopping, to avoid any imperfections that could compromise its strength.
When we are pouring, it's very important that the material is going inside the part with the right velocity. Otherwise, we can have oxides or other kind of defects that will appear.
It takes just minutes to fill the mold, but 2 days for the blade to cool and harden from over 1200 degrees Celsius. They remove the blade from its mold, then grind its surface smooth to make sure it glides through the water. A computer-guided rotating cutting head removes layer after layer of unwanted material.
It's very important that we mill these propellers precisely, otherwise we can have big imperfections on the surface. And this will affect to the performance of the propeller, and the passenger will be affected by that.
It takes 25 hours for the robot to glide over the blade thousands of times, polishing away every last defect to avoid a bumpy ride.
When we achieve the delivery, we feel very well, all the team.
Using propellers this large creates another big problem for engineers: keeping the ship maneuverable. The propellers on most ships are connected to the hull in a fixed position. To steer the ship, the captain uses a rudder. But this limits the vessel's maneuverability. For a cruise ship as large as Meraviglia, navigating through the tight ports at popular destinations would be near impossible. To solve this, the engineers must attach the propellers to 2 giant rotating thrusters, called azipods. These huge pods can spin round through 360 degrees. The rotating pods, together with small thrusters in the bow, should make controlling the ship much easier and allow this giant to breeze into the tightest of ports. Tipping the scales at around 170 tons, it takes 10 weeks to assemble a single azipod unit. The combined propeller and pod weigh nearly 200 tons apiece. Fitting them onto the vessel's stern will be a huge challenge. Any damage during the installation could set the entire project back by months.
The azipod for Meraviglia is like the legs. So if the legs not working properly, the ship cannot sail properly in the sea. So it's very, very important, the alignment, that everything is working perfectly.
The huge crane lowers the units down into the dock. Workers then carefully slide them underneath the ship before locking them into position.
So up to now the progress is good enough. Everything is according to the schedule.
With the pods attached, the hull of Meraviglia is finally complete. Inside, the vast 315-foot-long, two-story-high promenade that runs down the center of the ship is taking shape. But before the team can fit out the vessel's interior and install the cabins, workers must move the ship to a new quay. To do this, they must float the prototype vessel for the first time. This is a major milestone for the company bosses, who've arrived to witness the event. It takes 8 hours to fill the immense dock. Later that night, she's floating and ready to move. Meraviglia is so big, it takes 5 tugs to carefully tow her round to her new berth. In the shipyard's kitchen, Giuseppe Maresca is cooking lunch to fuel up his team, as work on the ship's interiors can finally begin.
Lunchtime for me is very important, because at the moment I stop my normal work and I start with something which is just relaxing and kind of creative. Our work is quite stressing and quite hard. We work a lot of time and long hours, and we have many responsibilities. Eating together and eating good can help us to keep the morale high.
Over the last 22 months, as the ship has grown, so has the team.
I came here 1 year ago and we were not more than 6 persons. Then slowly we increased. And now we are usually a cook today for 10, 11 persons, with a maximum of 16 once.
Complimenti a Peppino!
Giuseppe's team may be fueled up, but they'll have their work cut out installing the 16 cabin units that arrive from the factory every day.
It's a massive challenge to get all the cabins installed on time. From 6 in the morning we will have a truck coming here and cabins loading and loading and loading.
To keep pace with the relentless supply of cabins, Giuseppe and the team are using an ingenious technique to install. Special holes in the side of the ship provide access to slide the cabins on board quickly. They'll secure a giant lift onto the outside of the ship to reach them. They load and lift each cabin onto the ship. Special rollers allow the team to push the cabins on board, squeezing them through bulkheads and around tight corners, so they can slide them into the correct spot.
It's a bit like I'm wrapping a new Christmas present every day. This is where we get off. Stop! Push.
It's a tight squeeze to guide each of the 1.5-ton cabins through the maze of equipment and workers that cram the inside of the vessel.
One of the biggest problems is the space to put the cabin in position. It's every time like this. It's a lot of hard work.
If a single cabin gets damaged, it could hold up the installation of an entire deck of rooms.
All the works on board are connected, so we cannot have delay. This is inside of the cabin. Here we have the toilet, this is the wardrobe, and here we have the beds. There are no visible damage from the transportation. Yes, cabin is fine. another one done, and we have still more 1,000 to put on board.
While Giuseppe's team fire up the pace, on the lower decks, workers are racing to fit out the ship's cavernous promenade. This space is being designed to look like a Mediterranean-style seafront. The two-story high promenade will be filled with shops, restaurants and cafes.
Giuseppe, this is an Italian coffee bar.
Yeah.
Do you like to take a really Napoletan coffee?
Of course, I
do
it 10 times a day.
The first coffee will be for us, for sure, in this Italian coffee bar.
There's a huge amount of work for the team still to do. Their biggest job, installing the ship's giant LED ceiling.
The ceiling is the biggest LED screen in the world ever built in a vessel. The challenging will be to complete all the LED in time.
Instead of a standard glass skylight to cover the promenade ceiling, the team plan to break with tradition. They're preparing to install a never-before-attempted curved LED screen. It stretches 262 feet long and runs the length of the promenade. Installing it won't be easy. Workers must carefully piece together 1,450 individual LED panels to create the curved dome-like structure. Once complete, this LED screen will be able to display anything the ship's crew desire, changing the ambience of the entire promenade at the touch of a button.
The schedule for this area is very important because this is the heart of the ship. So without this room ready and perfect for the delivery will be a big problem.
It takes 3 months to install all 1,450 LED panels onto the giant curved frame. Thousands of cables connect the panels together. If just a single cable is incorrectly connected, the screen won't function properly.
Et c'est quoi, c'est l'image ou c'est la puissance? Alors, lequel vas-tu me donner?
With all the panels in place, it's time for the big test. Will all the sections of the 262-foot-long screen light up?
What we are looking at today is to have a complete and full image on all the vaults without any problem, without any pixel missing. Of course, the expectation of the owner is to have a perfect feature from the beginning to the end of the vault. So a very beautiful challenge for us. And let's see now what happens.
The video must be the same as the one of the flower.
But it's not long before they hit a major glitch.
Stop the screen and have a look to the small phone if it's working for the video. This is a mistake on the drawing. So strange. There is something that is not clear. We have one big black hole because there is a cable that is broken.
You set the configuration?
Yes. Nothing changed.
No. We are solving problem after problem. When you found a problem, you have to solve it and then go to the next step.
We have problem here because we never tested.
Yeah, and you didn't.
And here also.
Donne-moi un grand câble noir, s'il te plaît.
The team has finally fixed the glitches with the ship's unique LED ceiling.
As you can see, the video and the picture are sent correctly to all these LED panels. So yes, it's very good and we are very happy with this result.
There's now just 9 weeks to go until the cruise ship Meraviglia sets sail on her maiden voyage. But before they complete the fit-out, the ship needs to leave its berth for a crucial series of tests.
Very exciting, yes. It will be 3 days without sleeping for sure.
390 engineers, mechanics and crew are boarding the ship to take it out into the open ocean for the very first time.
Let's go on board.
Over the next 3 days and nights, they will put all its systems through a succession of grueling tests, called sea trials, to prove that the ship is safe to carry over 5,000 passengers. This is the moment that everybody has been working towards. It's make or break for Gaetano's team.
Meraviglia is a prototype ship, so the sea trial is the only moment where we can assess the performance of the ship. Of course, if we don't pass the sea trial, we cannot embark any passenger, we cannot deliver the ship, so we have to pass the sea trial.
The man Meraviglia must impress is lead inspector Jean-Luc Conneur.
It's the biggest ship I ever done on sea trial, sure. Là, j'ai tous les paramètres, si tu veux, des pods. The ship have to pass 100% of the test before they are able to taking passengers on board.
The team push the vessel to its very limit over the next 72 hours. They test its fire safety equipment. They assess how easily emergency crews can reach a helicopter and how quickly the anchor deploys. One of the most critical tests involves Luik's propeller. It must create no noise or vibration that could ruin the passengers' cruise.
We perform the test all over the ships, in all compartments and all decks, during the endurance test of the ships, because this is the most severe condition of the ship for vibration and noise.
While the ship sails at full speed, the team work their way from deck to deck, listening for excessive levels. Finally, they test the giant azipods that both propel and steer the vessel.
This is one of the most important equipment on board. We need 100% perfect to perform 110% of the power.
The crew will push the giant pods beyond their limits before undertaking a critical crash stop test.
So gentlemen, we are going to do crash stop test.
A crash stop involves using the azipods to bring the ship to a complete halt from a speed of 21 knots as quickly as possible.
The test will be done by rotating the azipod propeller outward first 45 degrees.
Okay, so we started by taking it to maneuver right now. Okay, crash stop!
This maneuver could be crucial in an emergency such as avoiding a collision.
Ship speed less than 19, 18, 17, 16, less than 15.
They spin the azipods into full reverse.
10 knots.
And the azipods are now in 180 degrees. Stop.
The mammoth vessel grinds to a halt in 4 minutes 49 seconds. But was it quick enough? After a tense few days and around 60 tests, the new prototype ship and her crew return to the shipyard. It's time for Jean-Luc to deliver his verdict.
This sea trial has been successful, really. And now the ship is ready to embark passengers, its first guests.
It's a huge relief for Gaetano.
The important test has been carried out and with the successful results. Now we have to just finalize all the remaining job.
Over the next 9 weeks, it's a frantic race to finish the promenade. Alongside workers, the entertainers practice their routines. And chefs fire up the kitchens as the clock counts down to the maiden voyage. Two years after work began on its construction, Meraviglia leaves the shipyard. Destination? The port of Le Havre in northern France, where the vessel will be christened ahead of her maiden voyage. But on board, the ship's still not finished.
In the indoor pool, there are some touch-up to be done on the handrails of the stairs, also all around the jacuzzi. The technical people are going around all the ship to check that everything is done. It's time now to be sure that the ship works and works well.
It's a scramble to complete the finishing touches as the ship closes in on Le Havre.
Now the pressure is very high because we have to finalize and close all pending items.
At Le Havre port, an events team prepare for the vessel's grand arrival.
Today is the day. The ship has reached Le Havre. Everything is finalized. All the touch-ups has been completed. We are very, very excited for this event. But the ship is ready, we are ready, and let's go.
As the sun begins to set, the stars come out. Celebrities, VIPs, and Executive Chairman Pier Francesco Vago gather to welcome the ship.
Ladies and gentlemen, I would like to thank the yard. They've done an amazing job creating the most innovative cruise ship today. Please join me to giving a big round of applause for all of the workers and all of them. Thank you.
In a time-honored tradition, the ship will be christened by a godmother. Tonight, actress Sophia Loren will cut the ribbon.
Et alors, il ne me reste plus qu'à souhaiter du fond du cœur à tous les futurs passagers de MSC Meraviglia un très, très bon voyage.
Are you ready? 5, 4, 3, 2, 1, go!
It's taken 3,000 people, more than 9 million hours of hard work to complete the first vessel in a brand new class of giant cruise ships.
Finally, the ship is ready, it's looking great, and I'm very happy that our work produced this. I'm very, very happy.
All our team are working very, very hard these 2 years, so we are very proud. And this my first cruise ship has been a very big challenge, but it's important that the result is good.
The following morning, the first passengers board and the ship sets sail on her maiden voyage around the Mediterranean. But only time will tell if the cruise line's huge investment building this giant will pay off. Today in Copenhagen,
60 centimeters.
this elite team of engineers is embarking on an epic endeavor.
This is one of the big tunneling projects in the world.
Hey Paul, this is Sybil in TV4. We can hear you loud and clear.
They're attempting to build an innovative £2.5 billion circular railway right underneath the heart of this historic city.
Now it's showtime.
Excavating 19 miles of tunnels through tough geology and toxic earth.
Carbon monoxide can kill you.
Starting to roll now.
With 17 brand new stations.
There are challenges ahead, challenges that everybody's willing to take on board and face.
And 39 driverless trains.
We've got a deadline. We need to achieve this fast.
This is the biggest construction project in the city for 400 years.
We are excavating one of the most important projects in Europe at the moment.
We cannot afford to cause any disruption to this station at all.
The team must battle catastrophic floods.
We need to stop this water as quickly as we can.
And collapsing earth.
Time-wise, we're right on the limit.
No, failure is not an option.
This massive underground railway ranks in a league of ambitious new engineering wonders that are bigger, faster, taller, and more advanced than anything ever constructed before. This series charts the inside story of the extraordinary challenge of building these giants. The historic city of Copenhagen lies on the east coast of Denmark. Its spectacular architecture and sights attract millions of visitors each year. But this creates a problem for the city's population. The capital's roads are congested. Copenhagen's 1.2 million residents have to battle daily tailbacks and gridlock that block major roadways. The city does have a metro, but built in 2002, it was not designed to cope with today's peak demand. So that's why, beneath the center of this historic city, this team of engineers is in the midst of building a trailblazing new underground railway.
It's pretty challenging and an important project because it is supposed to get 90% of the population of Copenhagen at less than 600 meters from a metro station.
Constructed in a circle underneath the city, the new railway, called City Ringen, will bring the majority of the population within a 10-minute walk to a station.
It's a project that is going to change the shape and face of the town once completed.
City Ringen will plug directly into the existing metro network to double capacity to nearly 130 million passengers each year.
How many rings this morning?
We already did one.
The man tasked with constructing the railway's congestion-busting tunnels is Valerio Violo.
The city of Copenhagen is looking at us. It is following the progress of the construction on a daily basis. They really want us to finish and to get the metro up and going. So there's a kind of a strong pressure on our shoulders.
Building a project of this magnitude directly beneath the heart of this historic capital city is no simple task.
There are a lot of safety challenges from underground works that come together, provides us with a lot of risk and hazard that you don't normally get in a normal construction of a building, for example.
This is the massive railway Valerio and the Copenhagen Metro team must somehow build. The plan is to construct 17 brand new subterranean stations that will circle the city in a ring. Each station will be unique, built to reflect its surrounding area. Underground at track level, platform edge doors will separate commuters from the 19 miles of freshly dug tunnels that will transport commuters around the city in minutes. 39 innovative driverless trains will run through the tunnels. Each train will have the capacity to shuttle 280 passengers between stations every 90 seconds. The new metro will be able to transport around 70 million passengers a year when it's complete.
It's going to be a big challenge because the city itself is relatively small and congested. So there are challenges ahead, challenges that everybody's willing to take on board and face.
Building the vast underground metro in this jam-packed capital city involves a series of key challenges. The team needs to excavate 17 massive holes right in the heart of the city. Inside them, they will build the sunken stations. To connect up each station, Valerio and his team must excavate 3 million tons of earth to create the 2 circular tunnels for the trains. Hot on the heels of the tunnelers, a team of track layers must position, concrete, and weld together over 22 miles of rail track. Engineers must also construct and test the fleet of 39 new driverless trains. One of the team's greatest challenges will be to construct the stretch of tunnels that must pass directly underneath Copenhagen's historic central train station, whilst it remains open.
This is the Italian headquarters. We have here the technical office where we control the excavation and the progression of the machines. We got a map here of Copenhagen. This is City Ringen. We are here and the City Ringen, it's completing the circle around Copenhagen and interconnecting in 2 places with the existing metro.
First task, construct the tunnels. These must be built before work inside the stations can continue.
We have 36 months to complete the tunneling. There is always the possibility to make a mistake in tunneling, and we need to be focused and to maintain our concentration.
As the son of a geologist, Valerio is no stranger to the underground. He has over 21 years' experience on mining projects around the world. But the City Ringen tunnels pose his biggest challenge to date.
I never had such a big project to manage and such a big company to manage all by myself. This one was a pretty challenging task.
To excavate the 19 miles of tunnels on time, the team is using a fleet of innovative digging vehicles called tunnel boring machines, or TBMs.
We currently have 4 machines working at the same time in this moment under Copenhagen.
Each machine is 344 feet long and is a mobile tunnel building factory. At the front, a giant 19-foot rotating cutter head claws away at the earth. The excavated material moves away from the cutter head on a conveyor. It is loaded into carts for a small train to tow away. A robot arm installs precast concrete segments to line the freshly dug tunnel tubes. It takes 6 segments to make up a complete tunnel ring, 4.6 feet wide. Hydraulic pistons then push the machine forward so the process can begin again. On average, each tunnel digging machine can install 18 rings a day as it snakes its way under Copenhagen.
We are looking at the TBM and the position on the map, and these lines are the tunnel to be excavated. The kitchen, they do split screen, recipe on one side and the TBM on the other side.
Tunnelers began work in 2013. And they've been digging non-stop ever since. The machines claw away up to 3,000 tons of earth, sand, and super hard rock every day. They allow the team to dig out and line an average of 3.7 miles of tunnel per year. Today is a crucial day for the tunneling team. One of the 4 machines has burrowed its way north to what will become Trianglen Station. Now it must break through into the half-built station structure itself, so that the tunnels and stations connect. Claudio Ramazzini is in charge of this critical part of the operation.
This is the break-in side of the station. Basically, as you can see here we have the concrete block, and inside of this concrete block we have one of our big tunnel boring machine, and is about to get in the station.
But that's easier said than done. To prepare for the machine's breakthrough, engineers have built a giant concrete block at the precise point where it will enter. The block acts as a plug to stop earth and groundwater flowing into the station as the machine eases through. Without this block, the pressure from the surrounding water in the ground could cause the wall around the machine to collapse, creating catastrophic damage.
The tunnel boring machine is about 11 meters inside the concrete block. If you get closer to the wall, you can hear the noise of the cutter head cutting the concrete.
For Claudio, the stakes are high.
We have to do the break-in on time to stay on schedule, so the teams here in Triangle Station can finish building the station.
Paul Evans heads down to make final checks.
Some of the concerns we have when the actual TBM literally breaks through that concrete is the possibility of debris flying quite a distance and injuring people.
But with the tunneling machine just 16 feet away from breaking through, the team hit a problem.
Va bene, okay.
Groundwater starts flooding into the station through a gap in the top of the concrete block, threatening the entire project.
We had a problem, we had a water inflow, so we had to stop the excavation.
We need to get this fixed quickly so we can proceed with the operation, the breakthrough operations. We don't want delay.
Groundwater is flowing through a gap between the outer edge of the tunnel and the platform ceiling. Unstopped, it could flood the tunnels. To stem the flow, Valerio's team must drill a ring of holes through the tunnel segments. The holes need to be at the precise point where the tunnel meets the station's exterior wall. Then they'll inject a special type of resin through these holes. The resin solidifies on contact with water and should form a watertight seal around the tunnel to plug the leak. Inside the station, engineers have begun battling the floodwater.
We are going to fix it by pumping out the water by 2 big pumps, and also we have a truck on surface sucking the water from the truck level.
It takes a frantic few days, working round the clock to make the station watertight.
The weekend was very hard for me, for everybody. We inject some resin, and then we stop the water inflow. Now we are excavating the last 80 centimeters.
Leak fixed, the team can now focus on the crucial breakthrough and hope that the resin plug holds up.
This is one of the most important parts of the project. Everybody's waiting. Everybody nervous and want to see the cutter head coming through the block.
The station team gather to witness the milestone. It's an anxious time for workers.
I've been waiting for 4 years for this machine to arrive on this side.
60 centimeters. Okay, now I'm going to call the pilot and say to him, restart and break in. Finish. No more delays. This is the moment of the truth. because we are with the tunnel boring machine. We have done the break-in, so great moment.
Success. The tunneling team break through and join up with the station crew for the first time. But for Claudio, the hard work doesn't stop here.
All the pressure gone now, just for a few hours, and then again pressure because we have to push the tunnel boring machine at the opposite, at the other side of the station.
With the tricky breakthrough behind them, the 4 TBMs pick up the pace.
I can see there's 2, yes.
The machines chew through nearly 3,000 tons of muck every day as they burrow underneath the city. Getting rid of all this excavated earth is another huge challenge for Valerio's team.
The TBM can build a lot of rings per day. Now, considering the distance, we are doing 18 rings per day in an average.
After the machine builds each ring, the excavated muck is carried away from the cutter head and dumped into a series of carts. Once full, a small train pulls them out to be emptied. Any delay getting rid of the waste could hold up the entire project.
If we are not able to empty these muck pits, it will of course have an immediately impact on the TBMs. This whole operation is vital for the whole project because we have TBMs running 24-hour day, 6 days a week.
But Copenhagen's unique geology creates a problem.
One of the big challenges was mining through contaminated ground. We had benzene, carbon monoxide and ammonia. We were not expecting it.
An old industrial part of the city has left behind a toxic legacy. This makes the task of managing the muck even tougher.
I'm taking some samples to be sent off for lab testing.
Every day, Christian's team must sample a trainload of muck for traces of contaminants. But he can't afford to hold up tunneling.
Both of these samples are together with the muck sent for analysis every day while the TBM is mining.
Workers empty the muck from these cars into temporary pits while they wait for the test results.
Every day we get the decisions from the authorities and then we instruct the worksite manager how they should organize the deposit and which muck pit is clean and which muck pit is contaminated.
It takes 24 hours for the results of each test to come through.
Hi Klaus. Where's the muck going today? It's clean?
It's clean muck.
Okay, thank you very much. All the muck today is clean and it's going to be disposed of to the clean soil facility. Maybe the situation is different tomorrow. We will have to wait and see.
Each truckload of muck travels 5 miles north of the city to this unique facility. This is no ordinary waste dump. Workers here are using the muck to extend the city out into the sea. They're filling in an area of the waterfront over half a mile square to create space for a new port and parkland.
The area is going to increase the area of Copenhagen by 1%. The soil area where we are right now is going to be used for the public in Copenhagen, for fishing, for having picnics, and for doing some kind of playing and whatever people like to do. Today it's a bit cold, I'm freezing, but when the summer is coming, maybe we can take a swim in the sea and do some sunbathing.
Underground, the tunneling team is still working flat out. They face the battle to drag the 700-ton tunneling machine through the platform so they can continue digging.
Everybody wants to see the machine come in, but then a lot of people want to see it leave again. because there's a lot of work that has to continue from there. There are deadlines to meet.
Claudio and his team get to work pushing the mechanical monster through the station.
Time is the biggest enemy for us because we need to get this through the station, restart mining, and stay on time.
Claudio needs to get the machine moving fast. The track layers are hot on their heels.
Valerio and his team with the tunnel boring machine are furiously chomping through virgin dirt. Our goal is to be as close as possible behind his team so that we can all finish this project on time. We have 2 tunnels, 17 stations. We've got a deadline. We need to achieve this fast.
Paul and the team need to position the track, secure it with concrete, and join each section together with absolute precision. It's no mean feat.
Just getting all that material underground is an enormous challenge in itself. Every bit of rail, every sleeper, every bit of concrete, it's not easy.
Working in the tight confines of the tunnel restricts the crew to only 1 carriage load of rails at a time, making this a mammoth operation.
It's imperative that these boys keep going. This is a 24-hour job, 58 metres a load. You can imagine how long it takes.
To help them install each piece in the right spot, they are using an innovative machine. This rail-laying gantry crane is fitted with precision grabbing arms to pick up and position the flexible pieces of rail.
There's a lot of skill involved in picking them up in the right position to minimise deflection. They do move around quite easily. They have to because the tunnel has so many twists and turns, it needs that flexibility.
The flexible rail helps the track layers snake a path through the curved tunnels.
With curvature in one direction, we also come across the problem of one rail getting longer or creeping ahead of the other. So every so often we need to perform a cut with a quick cut saw to make sure that we're back on level pegging.
They must level up the ends of the rail so that the next set of tracks join up smoothly. Any bumps or misalignments could derail a train.
This is definitely by far the most important stage of the track laying process.
Paul's team use a plumb line to help them push or pull the rails into position with pinpoint accuracy.
Without these sorts of accuracies, there's a chance that the train could derail. And if my head's sort of moving around like this, I may as well catch a bus. It needs to be smooth. Perfect.
With the tracks in place, the team must now lock them into position with concrete. That's easier said than done. To secure the next 50 feet of track, they need to pump around 20 tons of wet concrete 6 stories down to a mixer in the tunnels and feed it to the rail crew before it sets solid. It's a long distance in a short amount of time.
90 minutes is the time that we have to ensure that the concrete is still in a condition that we can use to lock the sleepers into their final position.
It takes over 40 minutes to fill each mixer.
If the concrete doesn't make it to its final position, we've got a problem.
The concrete is now already halfway through its lifespan.
There's an enormous amount of pressure on these guys. 90 minutes is not a long time.
The load reaches the concreting crew with just minutes to spare.
Time-wise, we're right on the limit. These guys have to work quick. Time is critical. The men in white just performing the final concrete finishing works by hand.
For this section of tunnel, it's job done.
Today, a good day. If we get 80 metres done, only 31,500 metres to go.
While work on both the tunnelling and track laying picks up pace, 1,200 miles away in Italy, engineers are building the railway's 39 new driverless trains. Here, the team assembles each of the train's 3 individual carriages, installs the doors and windows, and connect up the complex electrical systems that will provide the driverless train controls. Once built, each train is shipped to this test facility, where Davide Marandola's team add the finishing touches.
All the trains are my baby, so every time that come a new vehicle from the factory, I approach and then until I love it. From the receiving to the preparation to the testing until the final handover to the customer. I'm a really busy man all day long, yeah.
The new carriages are arriving thick and fast, so Davide has his work cut out.
Today is a very important day because we are going to test a new vehicle. For the first time we reach the test track, so it will be so important to get all the data to evaluate the behavior of the vehicle.
Hidden at the other end of the facility is Cityringen's high-speed test track, where each train must pass a series of critical tests. Today, technicians plug into Train 20's computer controls to track its performance.
We are going to test brake test and acceleration test. We are going to verify the situation of the vehicle we receive, if it's the good or we have to make an intervention. So we have to find out today.
Davide will push this train to its limit. It must accelerate and brake within a specified time and distance.
It's crucial because we need to provide a train that is reliable. And now we are going to the test track.
If this train fails, it could delay work on the entire fleet.
In the cab, we are using the emergency control desk.
When fully operational, the trains will be driverless. But for this crucial test, a driver sits in the hot seat.
Michael, can we get the forcing already? Yeah, so the acceleration is quite strong. Okay, now you can stop.
Now for the brake test.
We are starting, then when we reach max speed, we make max service brake.
Each train must be able to stop dead in 56 meters or less.
Okay, now you can stop. B3, yeah. Okay. Yes. Okay.
After a day on the test tracks, it's the moment of truth. Has this train passed both tests?
We can evaluate increasing of the speed, so this yellow line, from 0 to 40. The acceleration was 1.25, so has been good, reached in good way. The braking data, the distance we reach is 49 meters and the target has to be minor than 56. And the speed was 40.81, was fine. Yeah, is in good condition, the train, yeah.
It's back to base for this train, having passed with flying colours. But with 19 more trains to put through their paces, there's still a lot more work for Davide's team to do.
We'll start the next train, next job. New adventure, every train.
As trains begin to line up, ready to enter service, Paul's track team is working 24/7 to install the rails. With thousands of rail joins to weld, it's a relentless battle.
2 tunnels, 18 kilometres in length each tunnel. A weld every 18 metres. That's thousands and thousands of welds.
Paul and the team plan to use an ingenious and super fast welding technique to stop them falling behind. They are preparing a fiery chemical reaction to superheat a mixture of aluminium and iron oxide that creates a mix of molten metal. This liquid metal should fill the gap between the rails in minutes.
The advantage is the ability to join two unique bits of rail, creating one seamless stretch of railway line. Now it's showtime.
The chemical reaction is instantaneous. The liquid metal flows from the base of the drum into the mould. Any excess drains into these pans on either side.
It's critical that we wait the right amount of time before removing the moulds. If we remove the moulds too early, the metal will run and fall out of the joint. If we remove it too late, we run the risk of having molten metal stuck to the track, which is very hard to remove.
Once ready, they break the mould off and leave the weld to cool overnight.
Here we can see a thermit rail weld that was completed last night. We can see that the rail gap that we witnessed earlier is perfectly filled with the molten metal solution. It's had an initial grind and is ready for the final grinding later tomorrow. One rail weld completed, many thousands to go.
The super-fast welding helps Paul's team join around 590 feet of track a night. Across town, the team is gearing up to tunnel under Copenhagen's historic central station. This iconic station was built in 1911, and now 100,000 commuters use this crucial hub every day.
It's really important that we don't do any disruption to this, because this is the main hub for central Copenhagen and all the trains heading out to other parts of Denmark. So we cannot afford to cause any disruption to this station at all.
For the ring of tunnels to reach their final station, engineers need to tunnel just 49 feet below this busy hub. No tunnels have come this near to Copenhagen's oldest station before. And digging such huge holes so close to this historic brick-walled building, if not done right, could cause catastrophic damage and close this international hub for months.
Well, where we are at the moment is right next to Copenhagen's main central station. We have a 3-meter distance between the central station and the extremity of the work site. Just beyond that fence line is where the TBMs will come through eventually, passing literally 15 meters under the existing rail line.
The team is so nervous about digging this section of tunnel that they have a special crew that monitors the operation 24/7. It rests on the shoulders of Spiros Latsaneri to make sure the old station doesn't start collapsing.
We're in the center of this city, and it is very important that we monitor what is going on the surface and on the subsurface. The buildings we are passing below are very old, without foundations, most of them. So it is very important that we control very well our works, and we know that we do not create any damages that could be severe.
The plan is for workers to excavate the tunnels underneath the historic station. There's a real risk that the digging could disturb the earth around the machine, causing the soil to shift and triggering the buildings above ground to tilt. To monitor for this, Spiros and his team have installed a clever network of lasers and prisms all over the station to check for any movement. The laser fires a beam every 30 minutes to record the position of the prisms. If the spot the laser beam hits suddenly changes, this means that the prism has moved, and the system sends an alert back to base.
I'm watching very closely all data from TBM and all monitoring data gathered from the systems. So if there is a problem, I will be the first one to know and understand it.
Inch by inch, the machine slowly snakes its way under the main station.
Stop the foreman and just put it into the screw conveyor.
It's a tense time for the tunneling crew as they approach the point where they will make the final breakthrough next to the main station.
Okay guys, welcome.
It's the moment they've all been working towards.
We're working at night, preparing again. The main focus point today is going to be the final breakthrough. So of course it's not just a final breakthrough, it's the last breakthrough of the entire project. We've been part of this project now for the last 3 years, and it all comes to this point when it breaks through. We need to keep our focus on the safe distance for the spectators, and especially with this breakthrough, there's going to be a lot of people that want to get in there. There'll be a lot of eyes on us, and in that respect, we want to make sure that we do this, and it's a nice, clean breakthrough and without incident. Thank you.
But just as the tunnel has reached the halfway point under the station, some worrying readings alert Spiros' team to a problem.
There are 2 points that are recording settlements close to the alert limit due to probably the TBM passage, which are above the alert limit, but still they are close to that, so we will have to check it that it remains as it is and does not record more settlements, so it would be better that we have a team down to check it immediately.
The alert couldn't have come at a more crucial time. Spiros sends a team of surveyors to investigate if the settling earth is causing the platform's roof pillars to sink.
We had some points moving, and we're double checking to see if they continue to move or if they are staying in the same level, because the tunnel boring machine is right underneath us here, so we'll double check if it's all right. A lot of things could happen here. There's a very big arch over us, so if something happens with some of the pillars here, if part of the tunnel starts collapsing or something like this, we will know it before it gets critical.
They check all 60 prisons in the station, dodging commuters who are oblivious to the digging demon passing right beneath their feet.
Some days I can actually feel the boring machine moving under my feet, like vibrating the ground. Now I'll transfer the calculations from today. We can then see what was measured, and the 2 points that we measured that was close to the alarm levels are about the same height that they were last time, so they stopped moving down. Everything is stable and everything is where it's supposed to be.
The data confirms that the ground has stopped moving, at least for now. The tunnelers are clear to press on with the last push towards the finishing line and the final breakthrough into the new City Ringen station.
I think we should have them at this point here, rather than the bottom level. In my opinion, it's a bit too close.
Move back to 1
yeah,
meter.
we'll just move back a metre or two, so we have that little bit more extra space.
Hundreds of VIPs and officials are due to arrive to witness this momentous event. Paul can't afford anything to go wrong.
So tomorrow everything's going to be nice and clean and ready for the final breakthrough. Okay, I have no problems.
The team has enlisted some extra special help to make sure the final breakthrough goes without a hitch.
That's the statue of the Santa Barbara. She's the patron saint of miners. So wherever we go, we would like to have the statue there as a good luck symbol for our mining to keep us safe wherever we may be underground. She's brought us luck all this way, so why shouldn't she bring us luck for the final breakthrough?
After 3 years of construction work, the day of the final tunneling breakthrough finally arrives. Everything has been leading up to this crucial event.
The final act. Today is the end, at least of the tunneling operation.
We're all ready, we're all set up, ready to go. We're just waiting for the last of the visitors and guests to arrive, and then we'll get the all clear and we'll be ready to push.
31 kilometers, ending today, last meter.
With a subterranean feast, complete with champagne and red carpet all laid out, the pressure grows on the tunneling team.
There's a big buzz in the air and everyone's excited to see this happen.
Welcome to the last break-in of the project. We're going to go through a couple of safety
Inside the tunneling machine, Sybil Jensen gears up for the final push.
Sybil, this is Paul.
Radio check over.
Hey Paul, this is Sybil in TBM4. We can hear you loud and clear.
Okay, good. Everything looking good your side?
Yes, we checked the pumps. Everything is ready.
Thank you, stand by.
Everything's good to go on their side. Everything's how it should be.
Let's go.
Starting to roll now.
We can start pushing now.
Where start?
Piano, 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 piano.
With one final nudge, 19 miles of city ring-in tunnels are complete, and the 17 new stations finally connect up. For Valerio, Paul and the whole team, it's the end of an extraordinary underground journey.
How was that?
Oh, brilliant, fantastic, extremely happy.
For Copenhagen, it means that you can walk from here all around town and come back from that direction. A 15 kilometers ring is complete. It's the first big, huge step toward the completion of the metro. It's been a massive achievement for everybody involved. Everybody is so happy. Now today is just celebration. They're just celebrating what they did.
But just one final breakthrough remains to mark this huge achievement.
Buona torta! Have you seen this cake?
The last tunnelling breakthrough marks a key milestone in this ambitious £2.5 billion project. All the major civil engineering work is now complete. The team has poured more than 1 million tonnes of concrete, excavated more than 3 million tonnes of earth, and installed 135,000 tunnel segments.
We've done our job and we've done it very well.
31 kilometers, it's huge, it's very big. They really need to take time to process it.
Over the coming months, the Copenhagen Metro team continue to lay the last sections of track, fit out the stations so the ticket halls can open, and ready the 39 trains for operation.
When this is all finished, I want to come back and take the first ride on the metro. I'm definitely going to do that.
City Ringen will soon ease the pressure on Copenhagen's roads and help keep this historic capital city running well into the next century. Today in Atlanta, this team of elite engineers is embarking on an epic endeavor.
We're already out of whack.
They're racing to build a remarkable new superstructure. The world's most advanced sports stadium.
The scale of this is just gigantic.
Let's float this.
Constructed from more than 24,500 tons of steel and capable of seating up to 75,000 spectators. They're pushing to complete this ambitious geometric structure in time for the new football season.
On these big projects, there's always schedule pressure.
That's what this is all about, schedule.
To build this colossus, the team must battle extreme heights.
Man, it's an adrenaline rush, but ain't nothing that beats it.
And deadly winds.
As you're working in an elevated situation, wind gusts knock you off your iron. It don't matter how long you've been doing this. One mistake can cost you your life.
This super stadium ranks in a league of ambitious new engineering wonders that are bigger, faster, taller, and more advanced than anything ever constructed before. This series charts the inside story of the extraordinary race to build these giants. Atlanta, Georgia, a legendary sporting city of 500,000 people. Home of the 1996 Olympic Games and 2017 Super Bowl finalists, the Atlanta Falcons. To accommodate its growing legion of American football and soccer fans, the city needs a brand new stadium. When complete, this will be one of the most innovative stadiums ever constructed and will eclipse the old Georgia Dome. Soaring more than 300 feet tall and costing £1.2 billion, the brand new Mercedes-Benz Stadium will be the most advanced arena in the world.
It's such a unique, truly one-of-a-kind building. This is one of those projects that happens once in a lifetime.
Structural engineer Erlene Hatfield has helped design this boundary-pushing edifice.
So we had a lot of crazy ideas, and that's really what allowed us to push the limits and come up with this iconic building.
It rests on the shoulders of Avery Martin to actually build the stadium.
Part of the dangerousness of this particular project is nothing is forgiving. Everything's big. Everything has the potential to hurt you.
This is the giant Erlene needs Avery to somehow construct. Arriving through the main entrance, the heart of the new stadium. A vast 270,000-ton concrete bowl will hold 75,000 fans and support the 19,000-ton roof structure. From this huge frame will hang the world's biggest scoreboard, a 360-degree, 62,000-square-foot screen called a halo board. It will play in-game action and be viewable from any position in the stadium. Topping it off, the world's most complex retractable roof. It will be made up of 8 vast steel petals that must open and close within 12 minutes to stop bad weather ruining play. Designing and installing this roof will be the most challenging part of this ambitious build.
This is very, very complicated geometry. Nothing like this is even close to ever having been done before.
Stadiums with retractable roofs have revolutionized sports, giving fans year-round action. But the more complex the roof system, the more there is to go wrong. Montreal's Olympic Stadium, built in 1976, had one of the world's most complicated retractable arena roofs. But it ripped and failed over and over again, even when it was converted to a fixed roof. This is the kind of disaster the builders of Atlanta's new stadium must avoid at all costs.
I got what I get myself into.
Building this one-of-a-kind arena involves a series of key stages. First, the team must lay down the 18-acre foundation. Then, workers will build 19 vast reinforced concrete columns. This is all that will eventually support the roof. They must assemble thousands of precast concrete slabs to form its walls and floors. Then they must tie together steel trusses to form the base of the roof and fit the sliding petal panels on top. Inside, they must install 71,000 seats and the 616 sections that make up the giant halo board. Only then will they discover if the roof petals roll smoothly, closing to form a perfect seal.
What scares me the most, that when we go to push the button on the mechanization, that it doesn't all move perfectly.
The team begins building the 120-foot deep foundation and piecing together the concrete slabs to form the stadium bowl. It takes 19 months to assemble the arena shell. They construct the 19 concrete megacolumns around the perimeter of the stadium.
They're gigantic concrete columns. In a typical stadium, you might have 50 or 60 little columns that go all the way around the perimeter. But here, we're trying to reduce the number of columns to create a more open feel, better experience for the spectators.
The megacolumns will support the 15,000-ton roof trusses that are built out over the stadium bowl.
The longest truss spans 720 feet across the bowl from megacolumn to megacolumn. So they're quite big.
The roof trusses are so long that they erect these temporary 200-foot high steel towers to hold them up as the team assemble them right out across the bowl. With the trusses in place, Avery now faces his first real challenge. He must transfer the weight of the trusses onto the columns so he can take down the temporary towers.
It's going to be a nightmare.
This process is called the jack down. The big unknown, can the columns take the weight?
It would be like the domino effect. If one of these columns was to break in half, then you'd have every one of them follow suit. It would be catastrophe.
So this is the plan. Avery will use hydraulic jacks, positioned on top of the 4 towers, to lower the roof trusses down slowly onto the columns. The jacks will work in unison to gradually close 4 massive steel hinges at the top of each tower. These hinges will be under extraordinary pressure. As the hinges close, the weight of the 15,000-ton trusses should slowly shift off the temporary towers and onto the concrete columns around the rim of the stadium. Once the weight has been transferred, the team can remove the temporary towers and continue the build.
This is a big major milestone for us. To get where we're at now, it's been a long, hard road.
Time is tight. The stadium must be finished in time to host its first game of football, just 9 months from now.
There is a time pressure. I mean, on these big projects, there's always schedule pressure.
Getting the jack down wrong could set the entire project back months.
MC7 G5 trusses over here. Make sure the bolts are loose and take a radio with you.
It's 4 a.m. on the day of the big jack down. Avery's taking no chances and makes sure all bases are covered.
These are all names of individuals that I've got placed on each one of these columns. We're putting people at each location to make sure nothing binds up. Everybody's got to be on the same page. Everybody's got to keep their eyes open at all times.
The stakes are high. Timing is crucial. A sudden shift in weight could cause the hinges to buckle.
As we lower these hinges, everything opens up. So you need to pay attention to where your body is standing. Stay focused on everything you're doing. It don't matter how long you've been doing this. One mistake can cost you your life. Y'all don't mind, let's pray. Father, we come before you this morning. I thank you for this milestone that we've reached. I'm asking you for your guidance, your protection as we jack this roof system down. Amen.
It takes gangs of 5 workers positioned at the top of each 200-foot high tower to operate the jacks. This isn't a job for the faint-hearted.
Well, we gotta stay up here till it's done. That could be 15, 20 hours.
Once this comes down, they will not be able to put it back up. So it's critical that you pay attention, it's critical that you know what you're doing, and it's critical that you have clear communication.
All right, guys, it's time to go. Let's start jacking this thing down. Everybody make sure you get your hands and feet out of the way. Pay attention to the movement.
At the top of Tower 3, ironworker Dave Clacius retracts his jacks 4 inches at a time. Each cycle lowers the trusses by 1 inch.
We'll do it many times. I think about 15 times to get it down.
It's only going to close a ½ inch.
Avery must coordinate the teams at the top of each tower to lower their jacks at exactly the same pace.
How you doing, Henry?
We've been 50 minutes for 1 inch.
Go ahead.
We just need to maintain good coordination between all the towers, and it's just a slow process, slow and steady.
As the trusses drop down, these clever bearings that slide gently transfer the roof's massive weight onto the concrete columns.
This slide bearing is designed to move in and out as we jack this building down. It's going to allow this truss to move and flex.
It takes 8 hours for the team to reach the halfway point of the jack down.
Hey, coming up.
But with 7 inches still to go, they hit trouble.
Boy, we're getting heavy. Yeah, you're getting heavier too yet.
The jacks are overloaded, and the hinges are close to snapping under the enormous weight of the trusses.
Some of the ironworkers up on the top of the towers noticed that some of the steel is deforming. So they have stopped to take a look at what's going on.
We're going to have a long day.
The steel hinges start to bend. If they bend any more than a few millimeters, they could buckle.
The worst case scenario is that the jack would fail and the roof would come down very quickly.
We're not 100% sure exactly what's going on at the moment. There's no telling what could go wrong. So that's why we stop and make a plan to fix it. Where's that other? We've got crews moving and getting ready to start reinforcing on the hinge.
They will try to beef up the hinges by welding on extra thick plates of steel. Each plate is carefully engineered and sent up to the top of the towers. The crew work 24/7 to reinforce all 64 hinge arms with the inch-thick steel armor plates. The next day, they restart the jack down with trepidation.
Everything's going to be monitored and watched as we begin to jack this roof down again. Just one more step in the process of eating this animal. Pay attention to the movement.
The team keep a close eye on the hinges to check they hold up.
We just keep coming down until you see daylight, and then the truss is holding itself.
After an anxious 18 hours, touchdown.
The jack down is complete. It's awesome. It's awesome.
You know, this roof structure is so unique. It's awesome. It feels great.
With the roof trusses now resting on the concrete columns around the edge of the stadium, they can take down the temporary towers. This clears space inside the stadium bowl to erect the stands for the seats, fit out the interior, and build the retractable roof petals.
Major accomplishment. Now the hard work begins.
Over the next 4 months, workers pick up the pace. They piece together the geometric steel and plastic facade to create the stadium's show-stopping exterior. Inside, they install 1,100 tons of ductwork to feed the air conditioning system.
Atlanta is a very hot place. Can't imagine sitting for 3-4 hours inside a stadium without air conditioning.
They feed in 1,600 miles of electrical wiring and 60 miles of pipes to service over 1,500 toilets.
We're here in the middle of the bowl. There's 5 months until opening. It's very exciting. So the towers are gone now. The bowl's opened up a lot. You can start to feel the volume of the space. It's a much different environment.
The stadium is vast. Some fans will be almost 300 feet from the field and could struggle to see the action. So the next challenge is to build the world's biggest scoreboard. Instead of a flat rectangular scoreboard that's hard to see from every seat, they're breaking with tradition. Designing an ingenious scoreboard that stretches 1,100 feet right around the opening of the stadium roof. It will be made up of 1,848 massive flat-screen cabinets, each carefully angled to create the curve. Called a halo board, fans will be able to see this 62,000 square foot scoreboard from any seat in the house.
Now that the towers are out, you can see the curvature of the video halo. You can see the steel trusses that support the video halo. So the scale of this is just gigantic. It's the biggest scoreboard in sports.
But the sheer size of the scoreboard creates a unique problem for Erleen.
If we tried to use traditional flat screen technology for the halo board, it would be twice as heavy as what we have designed for now.
The solution is being developed 1,200 miles away in South Dakota.
We have not been asked to design or manufacture anything like the Halo display before.
Toby Pulsher has spent 2 years designing special lightweight screens that will fit together to form the scoreboard.
The definition is similar to what you would see at home. It's a high-definition display, except that you'll be sitting several hundred feet from the actual screen.
To create a high-definition video image the length of 3 football fields, Toby can't use traditional LCD flat-screen technology.
We had to modify our standard way of doing things to fit the requirements in terms of power and weight.
To build this screen, he will use 37 million light-emitting diodes, LEDs, almost halving the weight compared with flat-screen technology.
Essentially, your imagination is the only thing that limits the design and the size and the scope of LED displays.
Each LED has a fixed color, red, green, or blue. By grouping these 3 colors together, Toby creates a pixel.
By driving those LEDs at different intensities, making them brighter or dimmer, we can effectively produce any color imaginable.
864 LEDs make up one 14 by 14 inch panel. 23 panels are installed into one halo board cabinet.
So one option is that we could make the cabinets out of steel, but weight is a big factor. And steel is a lot heavier than aluminum. So using an aluminum cabinet saves on weight and saves on shipping costs and saves money overall.
Before the halo board can be shipped to Atlanta, the panels are put through hell.
It's important to test our components that they're going to stand up to those vast temperature changes, rain, snow. We do not want them breaking down at key moments during the big show.
Vibrations caused by the sliding roof could take their toll on the screen.
What we're doing is making sure that that display will be able to withstand the opening and closing of the roof.
Once tested, the 1,848 cabinets that make up the scoreboard need wrapping and packing for the long trip south. Before the team in Atlanta can install the halo board, they must finish the complex retractable roof. Next challenge, figure out how to open and close the roof in a super quick 12 minutes.
We're just going to go straight up with it.
I get asked a lot, are you really going to be able to design that? Can they really build something like that?
To keep it simple, the team could make the roof from 2 large sections that run on long sets of rails. But these roof panels would be heavy and take a long time to roll back. So Erleen's roof will be made up of 8 smaller panels that run along 16 shorter rails. The panels, called petals, are made up of 4 massive steel frames. Each 450-ton petal sits on 2 rails. The inner rail is just like any rail track. Sets of wheels attached to the petal will allow it to roll smoothly on top of the rail. But this won't work for the outer rail. As the petal moves out over the bowl, the back would lift upward as the front tries to tip. So they will position the rear set of wheels underneath the outer rail. This locks the back of the petal into the stadium roof. As the petal slides along the roof, the wheels will roll beneath the outer rail to stop the petal from falling.
Being creative in structural engineering is walking a very fine line. We have to figure out exactly where that fine line is.
Up on the roof, the team lays the rails that will hold the petals.
Good, everything's tied down, ready to go. Very nice.
While down in the bowl,
We don't have a shim on this side.
Avery oversees the construction of the vast retractable roof petals. The petals are too big to be built and lifted onto the roof in one piece. So they're built in 4 sections, a heel that connects to the fixed roof, 2 middle pieces, and the tip that slides out over the bowl. The bowl has become a massive factory, churning out petal sections.
It's relentless. It never stops.
This work site is crammed. As soon as a piece of petal is built, they must hoist it up into position on the roof to make way for the next one.
Good over there? Oh, Lord. Space. There's never enough space. As we built these things, these petals, it's crucial that every lift continues to follow the next one. Otherwise, number one, you can't meet the schedule, and that's what this is all about, the schedule.
Avery must hit his deadline. The stadium must be open in less than 5 months. It's critical that every piece of the roof is precisely the right shape and size.
Oh my God. We're checking every measurement, making sure everything's lined up, because once you go up with it up in the air, you're stuck with it for days while you're trying to get it fit up.
This side's low.
Need to come down 1/8.
The team gear up to lift one of the largest petal sections into place.
Got to come up 7/16.
And everything's looking pretty good.
With a storm due to blow in tonight, they're keen to get moving fast.
The weather has affected the schedule tremendously on this project. Just 2 weeks ago, we had 4 days of downtime just strictly for rain. When weather comes in, it shuts you down.
A sudden gust could blow the petal off course, causing it to crash into the stadium walls.
There's a storm coming tonight, and you'll have high winds, a lot of rain, so it's imperative that we get everything tied in and safe before we go home for the night.
Adam Castle coordinates the team on the ground.
All right, we're good. Once we pick it up, there's no putting it back down.
Danny Banks provides the eyes and ears up on the roof.
We do need to get it up in place, at least 50% bolted up before the weather does come in. There's an element of danger in everything. get complacent, go to hang over an edge, slip, whatever the case may be. There's always something. Most of us are pretty well at looking after one another. Yeah, that's the brotherhood of it. Heck, I spend more time with my partner out here than I do at home. So, they're family.
Let's go ahead and start cabling up. Nice and easy. Let it ride off this wood.
It takes America's biggest crawler crane to help Adam's team hoist this roof section into place.
Some of the ironworkers call it the beast. Big boy or Big Red. They call it Big Red. Yeah.
It's probably been called so many names that it's pathetic. But it's been an awesome crane to have on this project.
As the massive frame lifts off, scaffolding is still tying it to the ground. Adam works fast to wrestle it free.
Looking good. We'll let it ride off the end of this.
Two ground crews grapple the structure with ropes to stop it swinging out of control as it rises.
Hey, Gio, let off your side a little bit. Let's try to square this thing up a little more. The pitch looks real nice.
But halfway up,
We're already out of whack.
the tug of war between the ground crews falls out of sync.
You're fighting each other. You're just spinning this thing back and forth. Feed it through nice and easy. You don't have to pull on this thing. All right, hold that right there.
Adam coordinates the two ground crews, bringing them back into sync. The team regain control, and the petal continues its ascent.
Hey, Danny, you up there yet?
On top of the roof, Danny and the ironworkers wait to bolt the petal section into place as the storm approaches.
As you're working in an elevated situation, wind gusts knock you off the iron. It's got its hazards.
Construction workers that are up here, they're almost like mountaineers. They work at heights, they have special training.
Man, it's an adrenaline rush, but ain't nothing that beats it. It's the best thing in the world, man.
This is a dangerous, scary lifestyle, man. But that's what you get paid for.
I don't think I would be a very good iron worker, no.
Your typical everyday iron worker does have a screw loose. So it's all about glory. Cowboys in the sky, right?
It's a beautiful thing when a plan starts to come together.
Crane driver Andy raises the petal section the last 50 feet.
We look good right there.
Let me know when you're up at elevation there, Danny.
They have to get it above the catwalk, keep it even on both sides, all while walking in. This is where it gets tricky.
The big question, will this massive section of roof fit? If it doesn't, it's back to the drawing board.
We got about another 1.5 feet.
Andy must position the section perfectly so Danny's team can bolt it into place.
All right, we're gonna track you forward again.
Every one of the bolt holes must line up.
We drive pins through the holes to get everything to line up. You need everything to be square, plumb, everything lined up.
Easing down, about another foot. Tell me what you see.
Everybody's in radio communication.
Hold that.
Control of these pedals is critical. You can't let them go. You've got a catastrophe.
At the key moment, just as the team make their final adjustments,
I need slack in that tagline.
Danny's radio goes down.
Can you hear me, Steve? Can you hear me, Dave?
The storm is imminent. They only have one chance to secure the steel, or they must abort the lift.
They're not slacking off. They're just holding it.
Without comms, Danny can't direct the ground crews.
That's got this whole end out, which means it's over. We're See if you can tell them to slack off on that damn.
Can y'all slack off on the east side tagline some more, please?
Fortunately, the Brotherhood of Ironworkers comes to the rescue, helping Danny to regain command.
Can you hear me now? I hear everything.
There's a little bit of a radio malfunction. One of the mics stopped working, but the backup guy took over, and the transition was smooth.
Wrap that piece.
Finally, the first bolt is in.
Woo! Hold that.
And Danny can tighten the nuts.
We got 2 diagonals started. We're working on the third one.
After a tense afternoon, this section is secured, and Danny's crew can clear off the roof before the bad weather breaks.
It's attached, it's safe for the storm. If the storm does come in tonight, they don't have to worry about anything.
The ironworkers have another 23 petal sections to install over the next 3 months. As the roof team clock off, another crew clock on down below for the night shift.
Our target is tonight about 850 chairs, maybe 1,000 if we're lucky.
Gino's 14-strong team has been putting in the hours. They must install 71,000 seats. End to end, that's 23 miles of chairs. Each chair needs fitting by hand, but the overhead construction restricts where they can work.
It is the most complex project ever. It's the most cranes I've seen on a job ever in my life, which is causing a lot of delays, I think not on just us, but every trade. This is the first time we've had to really work nights for months on end to finish a project due to a situation on the job site. You got to do it to make it happen.
Yo, let's get these chairs out on the platform. Let's go. It's quick. This is one of the fastest systems in the world. You gotta be fit. You gotta have good cardio. You need everyone to come and give it what they got.
Adam's human chain can install 40 seats per minute.
We used to carry them up, but people's cardio would burn out. There we go. Now I feel it.
The chair is attached to an aluminium beam set into the concrete bowl.
After the beam's all installed, the chair just kind of slides in. This is a unique system because it clips into the beams.
By morning, the crew has installed almost 1,000 seats, which they've had to cover with fire blankets.
There's still an incredible amount of work going up on the roof. There's stuff dropping in, so they're trying to protect them the best they can, so they don't get chipped, broke, stained, melted.
1,000 seats down, 58,000 to go.
We're under a little bit of compression here at the stadium, so it's gonna be exhilarating, to say the least.
Everyone is feeling the heat as the countdown to the stadium's grand opening game reaches fever pitch.
Now the hard work begins.
The team building the new Mercedes-Benz Stadium has reached the final stage. Over the last 3 months, They've completed the exterior and built the steel frames of the 8 vast retractable roof petals. Inside, the seating is almost finished. Now they can begin to install the world's biggest sports screen. The 60-foot high, 1,100-foot long Halo board.
It's amazing how big it is and how much weight it is.
The giant screen was manufactured in South Dakota, made up of 43,000 LED panels, packed into 1,848 cabinets. With the cabinets now on site, the team must bolt them together into 14-foot high blocks.
No let out. We got to go full speed ahead, make our deadline.
Installing the 616 sections of the screen will take great skill.
We have a crew of about 15 guys. So when a section comes to them, they'll grab it, set it in place very carefully, and then they'll bolt them together. And then once they get it all aligned, we'll get it welded in place. On the face of course, you have the LEDs, so they can get damaged very quickly if you're not very careful.
As the 3,500-ton retractable roof closes, the steel holding the Halo board will move and flex. The delicate LED cabinets could be crushed together, damaging the screen. So the team has engineered 8 ingenious expansion joints into the Halo board structure. As the roof slides and the steel holding the Halo board bends, the joints absorb the movement, protecting the vast screen.
So we have one of our 8 expansion joints here, roughly 2.5 inches. When the steel moves, the cabinets will be able to move in tandem with that and not crash into each other. We're gonna feel really good once we get this one complete. I don't think I'll ever work on another job like this. This is definitely one of a kind.
This team must bolt 30 screen sections into place each day to stay on track.
They're expecting to see the fans in here real soon. Next thing you know, you'll have grass on the field, I guess.
The team face one final critical challenge before the stadium can open. They must attempt to close the world's most complex retractable roof for the very first time. This is a crucial test. The moment that everybody has been working towards over the past 3 years.
It's a big moment. It's a big moment. Everybody's excited, ready to get this thing closed up.
People ask me, can you really do that? Are you crazy? Can you get this thing to work?
We don't want any mechanical failures. It is very important that this test goes well.
All the petals must roll along their tracks together at the right speed. If any of the petals run at the wrong speed or have been installed at the wrong angle, the frames could collide, jamming the entire system.
Today we're closing the petals for the first time. This move is probably the most important move that will happen in the life of this structure. All 8 petals will move simultaneously. They have to move real close together at all times because at any moment they have to be within a foot or 2 feet of each other or else they'll run into each other. So we have to be very careful.
Andrew commands his 400-strong team to begin closing the roof.
3, 2, go.
96 motors power the wheels on the petals' inner rails, gradually driving the 8 vast steel roof sections. For opening day, the roof mechanization will be computerized. But for this test, they have to go old school.
We have to use tape measures. We don't necessarily know where all the petals are at once. 91 1/4.
91 1/2.
We'll stop at any big pop or bang or anything out of the ordinary, and we'll sound an alarm. 67. We're about 48% now from the closed position, so a little over halfway. 31.
The roof is almost closed. But will the petals meet in the middle?
11. Once those tips all come together, that'll be the closed position, and that'll be a success. We don't necessarily know where they're going to line up, so we're going to be watching how close they get and how well they align. 4, 3, 2, 1.
After a tense day, finally, success. The petal tips align. The world's most complex retractable roof is closed. Once the team has clad the petals, the roof should be watertight.
We did it. We are at 100% closed. It's a great feeling. The big step towards getting the stadium open. It changes the entire ambiance of the building. You know, it feels like you're in a different structure altogether. It's pretty cool.
It was awesome, awesome. A lot of nerve-wracking, you know, but never seen anything like it. When it's the first time something has ever been done, you look back and say, hey, I was a part of it.
Over the next 2 months, the team clads the petals with ultra-tough polymer sheeting. They lay the pitch and add the final touches before opening day.
And that building is going to be exciting to go to for many, many years. When you walk into it, it's not like anything you've ever seen.
After more than 3 years and a whole lot of engineering ingenuity, workers have installed the largest screen in sport.
This job is once in a lifetime.
And built the world's most complex stadium roof to complete the world's most advanced arena.
When I started this project, I never dreamed it was going to be a project of this size. This stadium has overwhelmed me. I'll say that. It's been overwhelming.
The Mercedes-Benz Stadium will see many close contests, but nothing that can equal the battle to build this giant. Today in Venice, this team of elite engineers is embarking on a unique endeavor.
It's never been done before.
With this ancient city under attack from rising sea levels, they are attempting to build a trailblazing structure, a giant ocean barrier.
It's a major problem, yes.
We have to start preparing right now.
Constructed from over 500,000 tons of concrete and 20,000 tons of steel. It's a race to surround Venice with this huge mechanical sea wall before its heritage is lost forever.
This sea is very aggressive. I'm losing Venice, I'm losing traces of my past.
To install this colossus, the team must battle extreme tides and deadly torrents of water.
Everything must come together perfectly.
This super sea barrier ranks in a league of ambitious new engineering wonders that are bigger, faster, taller, and more advanced than anything ever constructed before. This series charts the inside story of the extraordinary race to build these giants. Venice, one of the most iconic and historic cities in the world. It was established in 400 AD, built at sea level by the ancient Romans. Today, its architectural marvels and grand canals attract more than 10 million visitors a year. Venice lies 2 miles off the coast of mainland Italy and sits in a huge tidal saltwater lagoon. Sightseers, commuters, deliveries, even the emergency services, everyone and everything travels by water. But now, the water that makes Venice unique is causing its destruction.
It's very dangerous, and it could be a very critical problem for the stability of the city.
Salt water floods Venice up to 100 times a year, causing millions of pounds worth of damage. High tides combined with seasonal winds trigger seawater to inundate the city. With the flooding getting worse every year, the city urgently needs a way to stop Venice turning into a modern-day Atlantis.
Venice is one of the most amazing cities in the world. It's a magical city, full of historic buildings. It's a jewel for the world. We have to protect Venice from flooding.
To help solve the problem, Francesco Zago and his team of engineers are in the midst of building a trailblazing flood barrier called Modulo Sperimentale Elettromeccanico, or MOSE for short. MOSE also means Moses in Italian, and the significance of the biblical character holding back the sea is not lost on the citizens of Venice. It's costing almost £5 billion and has been 15 years in the making.
The MOSE project intends to save Venice, and the project has a life of 100 years. When it's forecast a high tide, we can raise the barrier and we can stop the Adriatic Sea and isolate the Venice city and the lagoon.
To stop the tides from flooding Venice, Francesco's team is planning to block 3 critical inlets that allow water to flow into the Venetian lagoon. Beneath the water, huge concrete foundations fixed into the seabed will support a series of massive steel gates. Before the tide rises too high, pumps will channel air into the gates. This will cause them to rise up to form a seamless barrier across the inlets that will keep the high tide out of the lagoon. When the danger passes, the gates fill with water and sink back down to the seabed, completely hidden from view.
There are 3 big challenges. It's a prototype. It's never been done before. It's under and above the sea. And everything must come together perfectly.
This is engineering on a scale that has never been seen before. For this plan to succeed, first workers must dredge the seafloor to excavate space for the barriers on each inlet. Then they must sink 27 foundation blocks, called caissons, precisely into position across the inlets. Then they need to assemble 78 individual steel gates that match the exact dimensions of the inlets. To carefully lower each gate down into position, they'll use a gantry crane, known as the grasshopper. The grasshopper must line up a male hinge on each gate with the female counterpart on the caisson. A V-shaped block on the caisson guides the crucial connection pin into place. They need to repeat this process perfectly 78 times in treacherous currents. This will be no simple task.
It's important to construct and to install correctly all the gates, and all the system has to work perfectly.
Work on Mose began in 2003 with the first stage of the build, laying the barrier's massive underwater foundation caissons.
Allora, com'è andata questa installazione?
Project manager Dario Berti oversaw the construction of the concrete caisson blocks and their installation on the seabed.
Construction of these big concrete blocks took a long time. Consider that one of these caissons has a weight of 23,000 tons. We had to perform a really huge operation.
Boats towed the concrete footings out into the channel and sunk them in a long line, up to 50 feet below the waves. Now the really crucial stage begins. With the foundation blocks in place, they must build and install the huge moving gates that will hold the floodwater at bay and save Venice. One of the most complex parts of the entire Mose project.
These gates have been manufactured according to the highest requirements of the international standards. Every gate is controlled with non-destructive testing. Everything is checked twice.
The gates are being built 224 miles away at this shipyard in Split on the coast of Croatia. The team of marine engineers here is more accustomed to building cruise ships. But their experience equips them with the unique skills and technology needed to build the giant underwater steel gates with such unparalleled precision and strength. Each gate starts life as flat pieces of steel. It's crucial that each piece is cut to perfect size. If the gates are just a fraction of an inch too wide, they won't fit snug into place. If the gates are not wide enough, they won't form a perfect seal against the tide. Water will leak through the barrier. A mismeasurement here would spell disaster for the entire Mose project. This machine helps them achieve the highest level of accuracy possible. It's a computer-controlled plasma cutter. First, the machine submerges each sheet of metal underwater.
We're cutting under the water because we want to reduce the heating, the formation of the pieces. We care lots about accuracy.
The machine uses gas, superheated to 10,000 degrees centigrade, to cut through the solid steel in milliseconds. The water cools the steel before it can buckle under the heat.
It works 2 shifts for 8 hours per day. It can cut about 300 meters per shift. It's a lot of cutting.
Once the components of each gate are cut to size, it's down to welding engineer Ivan Platzek to weld the hundreds of individual pieces together like a jigsaw.
There is around 15,000 different welds with different numbers on each gate. When you combine all this, that's around 40 kilometers.
With the team in Venice waiting on these 330-ton gates, Ivan uses an arsenal of robot welders to help keep up the pace.
This is fast and good quality welds. The welding speed is around 1 meter per minute.
The robots fuse the metal joints together at over 3,000 degrees, going over any cracks until the weld is perfect.
If the crack in the weld is not treated, that crack could expand and potentially could, the whole construction could collapse. That's really serious.
But as the gates take shape, their inside corners become too cramped for robots to access.
Robots cannot reach all the corners of the section, so they will never replace a human.
This is something that will be really hard for a robot to weld. So this is why you always have to have manual welding. You cannot replace everything with a robot.
It takes 5 months to construct each gate. The largest gates are 98 feet long and 65 feet wide. The team must perform one final critical test before they ship the gates to Venice. Quality control manager Ivana Zore must check that each gate is the perfect size.
If the gates are too wide, they will not be able to lift up and the system will not be operable anymore. It is one of the most important parts of the project.
They place targets at key points on the gates. The laser scanner then plots their position down to a fraction of an inch. Computers analyze the measurements to look for the slightest deviation from each gate's original blueprint.
So now with this test, we concluded that all the dimensions are according to the technical description. The gates are ready for transport to Venice.
They are wrapped in protective plastic, ready for their epic journey to Venice.
So it's an ideal moment to do loading operation.
It's 400 miles by road from Split to Venice, a journey that goes through mountainous Slovenia. To move the gates by truck, they'd have to close dozens of roads. So the team has no option but to tow the gates across the Adriatic Sea by barge. A huge challenge.
These gates are really heavy. They are 330 tons per gate. Inside, Milan will check his vehicles.
Milan Simic is in charge of loading the massive gates onto the barge for their voyage.
This is a big project in Italy, and it's also a big project for us. So we are really happy to save the Venice from drowning.
Each gate weighs more than a Boeing 747. All 4 combined weigh nearly 1,400 tons. Loading these hulks of steel onto this barge will be no simple task.
So we have these loading ramps here. We use them for crossing from the shore to the barge. And the gap is around 1 meter long.
Milan will mount the gates on these special multi-wheel transporters to shuttle them down the ramps.
They are working on hydraulic system. They are working in pair. Each can carry 300 tons. And in total, we have 600 tons of maximum load.
These monster remote control weightlifters are ready to roll. Once underneath, their super-powered hydraulics lift the gate from its supports. Each axle rotates independently and can turn a full circle. Ideal for precision parking these massive loads onto the moving barge. But just as the huge weight of the gate hits the floating platform, it starts to sink. Milan must act fast, or the barge could capsize.
The worst case scenario is that everything will end up in the sea, and we don't want it.
The 330-ton gate could easily tip the barge over. So they plan to use an ingenious system of ballast tanks inside the barge. The tanks are full of water. As the gate moves onto the barge, they must pump out exactly the right amount of water to offset the weight of the gate. As the gate moves along the barge, the team must constantly adjust the water in each tank if they are to keep the barge level. The timing is critical.
Grazie Franco, mandami Salvatore qui per favore.
If the ballast is not doing correctly, then we might have problems. Everything will collapse.
Franco da Luca.
Milan's crew must release the water from the barge at just the right moment. A miscalculation will be disastrous. They pump 87,000 gallons of water out of the tanks, and the barge levels up in the nick of time. Gate 1 makes it on board. The team carefully shuttle it to the far end of the barge to make room for the other gates. It takes 14 hours to load all 4 gates.
Grazie.
They weld the gates rigid to the deck to stop bad weather knocking them into the sea.
It's really necessary to secure on the barge because the waves can flip over at the gates.
After months of arduous work, this batch of gates finally heads out to Venice.
We have finished loading 4 gates today. The operation went good. We didn't have any problems. And we are ready to go to Italy now.
And not a moment too soon. Because even as these gates make their way to Venice, the water is causing devastating damage. Conservationist Paolo Pagnin knows only too well how the floodwaters are destroying the city and what can be done to restore its crumbling buildings.
Venice is under attack by water.
We are in front of Cadoro Museum, which is one of the most important museums of Venice. As you can see, the steps are 1 meter lower than the actual sea level. This tells you that the palace, when it has been built, the water was much lower. The sea level has risen.
When this museum was built 500 years ago, these stairs stopped at the water level. Today, the bottom step is submerged underwater all the time. Even small floods can have a massive impact on Venice's unique architecture. The buildings of Venice are constructed on wooden foundation stilts, driven deep into the mud beneath the sea. The Venetian architects laid a layer of Istrian stone and built their houses out of bricks and marble on top. The layer stone is non-porous and stops water from rising up into the walls of the building. But when the city floods, the water can rise over the stone, soaking the bricks and marble in salt water. Every time this happens, the salt erodes the stone, weakening the buildings.
This is the line of Istrian stone, which has the same thickness of the wall. This is the salt. Salt coming from the water. It crystallizes on the surface, creating damage and breaking the bricks. So all this is salt.
To the salt, nothing is sacred. It attacks Venice's most famous monuments. Restoring the city's world-renowned buildings, like the La Salute Church, is painstaking work. Here, conservationists are installing an underfloor heating system to keep the floor dry and free from future salt attacks. This arduous work requires skill and money. It is impossible to save all of Venice's structures this way. But with the floods getting higher and more frequent, Venice's buildings are deteriorating faster than ever.
I'm losing Venice, I'm losing traces of my past. I'm losing traces of our past. Mose has to work. It has to work. If it will not work, we will have more damage. We will have water rising through the walls. We will have more damage. So it has to work, and we are waiting for it.
As work on the barriers picks up pace, the wait is almost over. It takes 2 days for the delivery of gates to reach Venice from Croatia. Francesco's team is installing this set of gates at the Malamocco inlet.
Allora, ciao. Andata bene anche questa, eh?
This is the deepest of the 3 crucial inlets that the Mosè barrier must seal off from the sea.
We are here in Malamocco, and this inlet is the most difficult inlet of the Mosè project because of the water depth in this inlet is 14 meters. These are the most difficult conditions for installing the gates. Francesco is leading the operation. He has a very, very high capability of sustaining stress.
Francesco will direct the mission to install each 330-ton gate from this special control room.
Max? The coordination between all the teams are crucial for the success of the installation.
They plan to use this innovative crane to sink each gate down into position onto the underwater foundation blocks. They call it the Grasshopper. 800 tons of steel, equipped with 4 ultra-strong hydraulic jacks that grip and release winch cables to lower the gate down. Workers load each gate onto a barge and maneuver it right underneath the Grasshopper's belly.
Mi fai vedere i dati alla bottiglia un attimo?
Francesco must direct the crews working on both the Grasshopper and inside the foundation caissons, 85 feet under the murky water, to line the gate up as the crane lowers it down into place. There's close to 0 visibility underwater, so the divers must place cameras on each socket to help Francesco guide the teams towards touchdown.
Quanto manca al touchdown con l'acqua?
Any unexpected movement could damage the gate catastrophically as it nears the caisson. The gate is so heavy that if it drops too fast, it would cause a piston effect in the water beneath, pushing a column of high-pressure water into the connecting hinge. This could puncture the gaskets of the hinge and cause seawater to flood the caissons and threaten the workers inside.
Dario is very worried about damages. This is the reason why we spend all our energies to plan the installation.
This is the critical part of the operation Francesco's team has been working towards for 15 years.
The plan is to install the gate. All the team now is very concentrated to reach the target. Ok, Max, possiamo cominciare con la discesa.
It's an anxious time for the team as the Grasshopper starts to winch the gate down.
Mi puoi tenere aperta la cosa? Siamo un po' storti, sembra. Max, puoi andare 50 millimetri lato sud con la paratoia?
The Grasshopper's 4 jacks must operate in perfect unison to keep the gate level as it descends. If any one of these cables runs too fast or slow, they could tilt the gate, and it won't line up with the foundation blocks underwater.
Currently, the gates are almost perfectly positioned.
But just as the hinges of the gate and blocks get close to lining up, they hit a glitch.
Look the crab there on the camera. And you can see also the male approaching the female now on the camera.
An invasion of crabs overruns the hinges.
All these things, all this environment can affect the installation.
Luckily, the strong Malamocco current soon clears Francesco's line of sight.
Mad crabs. They go everywhere.
They are now just 3 feet away from locking the gate into the caisson.
We can see on the screen the iron pin that has to go into the V-shapes, the female element. We are very close to the touchdown.
A misalignment now would cause catastrophic damage. Francesco reduces the descending speed of the gate to line the hinges up for the final approach.
Inizia a fare I controlli, dai.
But inches from touchdown,
Max, fermatevi,
Francesco spots another problem.
Siete scesi a siluro.
The gate is dropping much faster than he wants it to. A runaway gate could force a huge amount of water down as it descends, damaging the seals and gaskets around the caisson that protect the workers inside.
Lascia che ci ragioni un po' sopra perché non capisco come mai.
Francesco calls an immediate halt. He orders the gate to be lifted up again so he can try a slower approach.
We have to go down in the correct position, slowly. No human error, no mistakes now. Now we can see on the camera 3 and camera 4, we are on the target.
Touchdown.
Paolo, ti confermo, noi siamo in touchdown. Adesso cortesemente attendo tue notizie.
Francesco thinks this operation went well, but he won't know for sure until the team inside the caisson give the thumbs up.
We have to wait a few minutes to understand if the touchdown is gone well.
Ti confermo anche dal camera 2. Non ho perdite in nessuno dei due.
Ok, bene.
Bravo. Iniziamo meglio.
Okay, the touchdown was perfect. We're very happy. The installation of the gate is done in a very good way.
It's a successful operation. But some areas of the Venetian lagoon simply cannot afford to wait for their arrival. 15 miles south of Venice lies the small town of Chioggia. It's built on a network of canals, like Venice. The flooding here has become so frequent that the buildings could be irreparably damaged before Francesco's team has the Mosè barriers in place. Engineer Fabrizio Pavanello was drafted in to construct an emergency flood barrier to buy this fast-submerging town some time. His solution was this, an ingenious baby Mosè.
Il baby Mosè, come abbiamo detto prima, evita che tutto il centro storico si allaghi. Cioè, evita che, siccome si allaga a circa 90 centimetri, allora, questo è il canale principale della città di Chioggia ed è fondamentale chiuderlo per fare in modo che il centro storico non si allaghi.
Fabrizio realized that he could save most of Chioggia by stopping just this single canal from flooding. To do this, he built 2 simplified gate systems, one on each end of the canal.
Abbiamo dovuto rinterrare tutto il canale, fare tutte le paratie micropali e è stato un lavoro molto duro.
Most of the time, the barriers rest hidden on the seabed, just as the larger Mosè gates will. When a high tide is predicted, 2 hydraulic motors lift the barriers in just 8 minutes. Protecting just this one canal has taken years of work.
Certo, è stata una cosa semplice, cioè sono stati 6-7 anni di lavoro.
The baby Mosè has worked for Chioggia, holding the devastating floods at bay. But using this system to block every canal that threads through Venice isn't practical.
Perché qua a Chioggia abbiamo solamente un canale da isolare, mentre a Venezia dovresti farne un centinaio, 200 di baby mose, perché ci sono tantissimi canali. Ecco perché Venezia ha bisogno di una soluzione più imponente e diversa da questa.
For Mose to succeed, its operators not only need to be able to hold back the floods, but also predict when they will occur. This control room is the brain of the flood barrier network. It's where project leader Dario Berti will decide when to raise the floodgates, once they're all in place and operational.
It is essential for us to have the reliable information for operating the Moses system.
Dario's team must raise the barriers before the tide rises for the system to work successfully.
You need to predict what will happen in time, because we need to start mobilizing well in advance. I need to know one day before what will happen the day after.
The detailed sea level readings Dario needs to raise the barriers at the right time come from this oceanographic platform. It sits 10 miles outside the Venetian lagoon. Fabio Trincadi's team of scientists regularly visit the platform to test the accuracy of its readings.
In the Adriatic we have many points. This is the most important and the most instrumented. This is most vital for Venice. The exercise we do is to check constantly. We predict every day the water level, and every day we have the measurements here.
The instruments here feed data on the water levels, wind speed, air pressure, and wave height back to Dario's control room. Back at the Malamocco inlet, with 7 of the 19 gates in place, the team start work on the final set of floodgates for this barrier. Francesco's team make their final checks before they begin to install them.
Yeah, 3 millimeters, Sandro. Ancora, ancora, ancora. Okay.
But gate engineer Dino Balic spots a problem with this gate that could shut down the whole operation.
Here we have damages. This is also from the protective foil. First gate, when they put here, they didn't count on seagulls. They start to eat silicone. They are pretty strange animals.
Seagulls are attacking the gates and scraping away the paint.
Seagulls are damaging the surface of these gates. They are looking for food, you know, and they used to pick the plastic bags. And the gates are covered by tarpaulin, which is looking like a big plastic bag. And so they consider that this could be a very big bag of food. They damage the surface to the metal. They destroy the anti-corrosive protection.
The paint defends the metal gates against the corrosive salt in the sea. Even the smallest scratch will cause the gates to rust.
When it starts to rusting, it will be disaster. It will be all rust, the paint will fall off. It will be pretty ugly to see.
The teams repaint the exposed areas by hand to keep the build on track.
We have 5 coats, on some places even 6 coats of paint.
And devise a clever way to keep the birds at bay.
You have here speakers, and you have these strange sounds, and they don't come anymore. We have a complete jungle to frighten the seagulls.
With the birds scared off, This last-minute paint job should protect the gates from the destructive forces of the sea. Now the team must install the remaining gates. Engineer Francesco Zago has installed 7 of the 19 floodgates that will block the Malamocco inlet. While he has good weather, he wants to get the last ones in without delay.
Please check all the valves.
Francesco is 85 feet below sea level, inside the gate's underwater foundation caissons. He's making final preparations to drop gate number 8 into place above.
Everything has to be ready when we make the touchdown with the gate. Also here, all the connections are good now. Okay, this unit is okay. Yeah.
To install the gate, first they need to move the enormous gantry crane, the Grasshopper, into position over Gate 8's drop zone. To do this, they'll attempt to steer a barge carefully into place underneath the crane and secure it using steel cables anchored to the seabed. They'll attach special jacks to the Grasshopper to lift it up. Then haul the barge to the new position, carrying the crane on top. The jacks will then slowly lower the Grasshopper down, so its feet sit back on the seabed. They'll then move the barge so the crane can pick up gate number 8 and lower it down into place. That's if all goes to plan. It takes great skill to guide the barge into place between the crane's legs and connect up the lifting jacks.
Quando smonto da qua, passo da te.
Now the next operation is to lift up the Grasshopper from the caisson and to move on the next position.
Va bene, prosegui.
The jacks slowly lift the crane up onto the barge. But just as they start to move the barge to the next position, one of the cables pulling it across the water jams.
The winches on the barge are fundamental to position the barge. It's not possible to move the barge and the Grasshopper if one of the winches is broken. It's a major problem, yes.
It takes some serious muscle power to wrangle the cable free. They use computers to move the crane into place right above Gate 8's drop zone.
Now we are over the position and we need to lowering down the Grasshopper on the caisson. We need to be perfect with the precision of the installation.
Bravi ragazzi.
The Grasshopper is perfectly on caisson and the operation now is closed.
With the gate connected to the crane, they lower it down onto the foundation caisson. Once it's in position, there's one final challenge. The currents in the Malamocco inlet are so strong that they could dislodge the 330-ton steel floodgates. To hold them steady, the team planned to thread a special anchoring rod through the hinge from inside the caisson. The anchoring rod will reach right up into the hinge, twist 90 degrees, and be pulled back down with a force of over 300 tons. If successful, the gate will be securely fastened to the caisson.
Yeah, okay.
Dario Berti is inside the caisson to make sure nothing goes wrong with this crucial stage.
It's an important moment because if something goes wrong, we have to start again. The consequence could be that we have to remove the gate and perform everything again. This element is entering into the male connector. And now they start with the rotation, which is rotating and getting to the 90 degrees position.
With over 300 tons slowly pulling down on the hinge, any defects will crack the housing and the gate won't be secured to its neighbors.
No leaks.
After a tense few hours, gate number 8 is firmly locked into place.
This is another Malamocco gate installed. Operations went well. Everything is in place and up and working. Now we will celebrate with a beer, with a glass of wine, with slicing a ham, and celebrating this. Yeah, it's a big day today.
Now we have to celebrate the great installation of today, so it's a party moment, but only 10 minutes.
Over the next few months, Francesco's team make headway installing the rest of the gates that make up the Malamocco barrier. After 15 years construction work, 2 of the 3 Mosè barriers that will block the flow of water into the Venetian lagoon are complete. Work sealing the last inlet is due to be finished within the next 3 years. The team is already running operational tests on the completed barrier sections.
In a matter of 40 minutes, we are in the possibility of closing all the inlets of the lagoon.
When they press the button, the 98-foot-long gates fill with air and lift up to hold back the Adriatic Sea. Ready to protect Venice from deadly deluges. The team here really have achieved something remarkable.
With all the barrier here installed, we will be one step closer to save Venice.
We have completed the installation of the gate. Yeah, I'm so proud.
Many people thought the day would never come when the Mosè flood barriers would work.
Even if the Venetians can adapt, they can wear the boots, but the buildings cannot. So the Mosè, at the end, will save the city and their inhabitants.
The Mosè flood barriers will battle the high tides around Venice for decades, saving this historic city for many future generations. Today in Barcelona, this team of elite engineers is embarking on an epic endeavor.
It's like magic, no?
They're attempting to build an extraordinary and complex superstructure. The world's tallest church.
When the towers will be finished, the skyline will change.
With a unique, untested construction method, using more than 170,000 tons of stone. When complete, Sagrada Familia will soar more than 565 feet tall and become one of the world's most boldly designed churches.
It's a big project, unique.
I walked in and it was like goosebumps.
To build this masterpiece, the team must battle deadly winds.
A strong wind can take down the crane.
It would collapse, so it just isn't an option.
And extreme heights.
We can lift. It's impossible. You are crazy.
We cannot afford any delay, any disaster, any mistake.
This incredible temple ranks in a league of ambitious engineering wonders that are bigger, faster, taller, and more advanced than anything ever constructed before. This series charts the inside story of the extraordinary race to build these giants. In Barcelona, one of the world's most historic and beautiful cities, workers have been laboring across 5 generations to build one of the most architecturally complex churches ever conceived. Sagrada Familia. Only partially built after 135 years, and soaring 330 feet tall, this awe-inspiring church already attracts 4.5 million visitors a year.
You'll come in and it'll take your breath away like this, but it's still not done yet. There's so much more to be done, and obviously outside you see the cranes doing building work, and so it'll be interesting to see how it turns out when it's finished.
But now, the end of this extraordinary build may finally be in sight.
We are going to be the last generation finishing this project.
Building work began on this ambitious church in 1882. Workers first built on the foundation of a traditional Gothic crypt. The temple's nativity facade, with its 330-foot-high bell towers, were finished in 1936. It's taken over 50 years to build the epic Passion facade. Then construct the vast central nave, vaulting and transepts. To form the launchpad for 6 mighty towers, yet to be built. Today, they're attempting to finally complete this giant, using the funds generated by the 12,000 tourists that visit each day. Following in the footsteps of generations of architects before him, Chief Architect Jordi Fowley has been building up his dream team in the race to finish.
When I started my work here, only there are 6 people in the office. Now, 40, because it's a big project, unique.
Jordi's biggest challenge, complete the basilica with barely any plans. Sagrada Familia's original visionary architect, Antoni Gaudi, died almost 100 years ago, and few blueprints have survived. It's a great engineering mystery. They've got this far by copying old photographs of models and 100-year-old sketches.
It's important for us to be faithful to Gaudí, because Gaudí was a genius.
Gaudi was a true architectural maverick, pioneering unique geometric forms, inspired by the nature around him, trees, animals, mountains. He worked in a style never seen before or since.
Gaudí considered himself as a collaborator of God. The architecture of Gaudí is architecture with life, with natural forms, with color, different from another architecture.
This is Gaudi's vision, the giant Jordi and his team must somehow complete. Three huge facades will tell the story of Jesus. representing his life and teachings. 6 enormous central towers will almost double the height of the temple, making it the world's tallest church, at 565 feet tall. Costing an estimated £900 million and almost 145 years in the making, Sagrada Familia will be one of the world's most extraordinary structures.
Now we are focused in the construction of the 6 central towers. When the towers will be finished, the skyline of Barcelona will change.
Completing Sagrada Familia involves a series of unique engineering challenges. They plan to raise the towers in levels, formed from pre-assembled panels. Most panels will be made up of 16 blocks of stone. The team must construct spiral staircases inside 4 of the towers as they rise up. Elaborate stone friezes and exquisite stained glass will adorn the larger towers. The team is aiming to complete the Sagrada Familia before the centenary of Gaudi's death, just 9 years from now. The first challenge: source the stone to build the towers and facades. Gaudi's workers used local stone from the mountain of Montjuic, a unique multicolored stone.
You can see a stone of Montjuic can be red, can be gray, can be kind of yellow, close to orange, brown, dark gray. That gives a very rich colored wall.
But Jordi's team has a massive problem. The Montjuic stone quarry is now closed. So they must find a way to replicate the look of Montjuic stone.
We need to get the same concept as Gaudí. In the case of the towers, we decided to mix different kinds of stones with different kinds of colors to try to reproduce the same wall. This is like pixels on the TV. If you get so close, you see every pixel on every color. When you go out, you see one uniform color. We have to create this effect on the towers.
So Pau is sourcing the stone for the towers from 70 quarries around the world. Granite blue Bahia from Brazil, red porphyry from Iran, and the only quarry that can deliver the right shade of light brown buff gritstone in Lancashire, England.
We've had a call from Barcelona wanting to supply stone to the Sagrada Familia. We thought it was a hoax, to be honest. We thought it was a joke.
Quarry manager Emma Armstrong must deliver over 300 tons each week for Sagrada Familia.
The quality of our stone is absolutely critically important to the project in Barcelona, because if it wasn't of the strength and resilience as it is, basically the towers wouldn't stand up on their own, they'd collapse.
It takes great skill to extract this high-grade stone. Creating even the tiniest fractures inside the rock could be disastrous for the towers.
We do not want to make any fractures. We cannot have any fractured rock because obviously that would affect the strength and would create a weakness in the rock. What are we up to next, mate? What's next stage?
Naturally occurring hairline cracks run through the rock. Emma's team will cleverly use these existing fissures to break the stone out.
So it's taking this corner out, basically.
Just checking that out to get back.
And then what you weigh.
To extract every ton of gritstone for Sagrada Familia, Emma is relying on blast engineer Mick Tootle.
We say there's no pressure, but all down to one man, little Mick.
You're going to drill an hole and then you put your charge in. It's very low explosive, but it won't do any more damage than what the rock's already got originally. It's delicate touch to it, rather than a massive blast. That's the beauty of it, like.
The explosion frees the 10-ton block. Now Mick must carefully tease it away from the rock face.
Or it'll be like a tooth. It'll be jammed in and you'll have to riddle it. You want it intact, fracture-free as you can. It looks all right to me. You can't see any airline cracks in it, so it should cut all right. And then off to Spain. And then they can put it in the cathedral.
Mick and Emma must deliver almost 120,000 tons of stone for Sagrada Familia. Every block must be flawless.
We do go as fast as we can, but it is a very precise process and it's something that can't be rushed. Being a small family-run business over here in Lancashire, it is quite humbling, but also very satisfying that we're supplying the stone to complete the most photographed religious monument in the world.
The stone is shipped to this yard just outside Barcelona. Before they build the towers, Fernando Villa must check each batch of stone is strong enough to keep the towers from falling.
Sagrada Familia is forever. Our responsibility is to make sure that this stone is forever too.
Fernando's team drill out a core sample from the stone.
This test is to crush the piece.
Each of the tower's stones must be able to withstand at least 15 tons to be strong enough to become part of the structure. Using a stone compression testing machine, they increase the pressure.
"30 tons, the pressure on the piece. It's amazing. It's the double of we need. It's not possible that tower falling down. It's not possible.
The stone passes the test. Now they can start work erecting the 6 central towers. It's taken over 3 years of detective work to figure out exactly how to design and assemble the tower's intricate stonework. That's because the tower's height and dimensions were a complete mystery. Few clues survive, such as this silhouette sketch created in the early part of Gaudi's life for a completely untested design that seemed to defy physics. This is one other clue that the team had to go on. A model built around 100 years ago. The model is of a small squat tower called the sacristy that Gaudi designed to be built at the rear of the basilica. The sacristy also holds the key to the shape of the church's 6 main towers. Architect Esteve Humbert has been trying to unlock its secrets.
These small bits belongs to the original model. Just by having a small bit of a surface, we could reconstruct the whole thing.
Esteve's team used the model to build the full-size 130-foot-high sacristy tower. It's grafted onto the west side of the basilica and is home to Sagrada Familia's team of architects.
We have 4 main disciples of Gaudi who worked and lived at the time he was working here in Sagrada Familia. So Gaudi talked to the followers or the disciples to use the sacristy as a template for the main towers.
The secrets of the main tower's dimensions are contained in the geometry of the smaller sacristy tower. So Esteve uses powerful software to reproduce the sacristy geometry.
So what we have to do was to stretch the geometry of the sacristy to be able to build the main towers, just by changing its proportions.
He designed the towers following the Gaudí drawings and following also the model of the sacristy that contain the way to design the towers.
Meticulous detective work may have revealed the blueprints for the 6 towers, but building them will take some ingenious engineering. In the beautiful, peaceful Catalonian countryside, the tower's construction is well underway. The church's city centre plot is crammed, so workers pre-assemble sections of the towers at this open-air site 50 miles away.
Here you can see it's like a factory. Here we build the Sagrada Familia.
In charge of turning the architect's plans into reality is veteran builder Jaume Torreguitart. He's working out how to build the towers at high speed.
We have to use a new technology. We don't need to work like 100 years ago.
Hoisting every stone for the towers up to the top of Sagrada Familia individually would take almost 50 years and require around 14,000 separate crane lifts. So Jaume's team plans to build the towers in small sections called panels. 16 blocks of stone make up these panels. 8 panels make up one tower level. Once a level is completed, Jaume's team needs to truck the panels to Barcelona. On site, they plan to use a crane to hoist them up to the top of Sagrada Familia and slot them into a steel frame. This clever technique should allow them to construct the towers 16 times faster than building them block by block.
We will build the next 3 years 836 panels. It's a lot of work in less time.
Jaume's team is at a critical phase. It's building the first panels for the first tower. They assemble each panel against this green frame. It ensures that all 8 panels fit together perfectly.
In this panel there are 16 stones. We put the stone in his correct place, put the mortar, and it would be in his place forever.
4 bolts will lock the panels into the steel frame on the tower. During installation at the top of Sagrada Familia, 250 feet above Barcelona, every bolt hole must align to the millimeter, or the panels will be left hanging.
We work with only 1 mil of tolerance in all of this piece. If we can't fit them, it will be a very, very, very big problem.
Surveyors use lasers to check the dimensions of each panel, to be sure the bolts will fit and secure the panels in place on top of the tower.
If we have any difficulty to introduce the bolt, disaster, obviously, we cannot afford any delay, any disaster, any mistake in our construction.
It takes 3 weeks to build the first level of panels for the first tower. But will they align? The batch of panels survives their cross-country trek and arrives in Barcelona undamaged. Today is the day of the big lift. This is the ultimate test. Jaume's team must hoist each 7-ton panel 100 meters to the top of Sagrada Familia. slot them down into a steel holding frame, then bolt them into place. Only then will they discover if the bespoke construction theory works in practice.
Well, today for us is a special day. For us is a proof, because it's the first time that we are going to assemble this piece in its correct place.
Jaume's crew secures the first panel to the 140-meter high tower crane built into the basilica.
Y un poco carro atrás.
They hold their breath as the lift begins.
We are going to assemble the first panel.
Jaume races the panel to the top of Sagrada Familia to oversee its installation. Lining the panel up with the tower's frame on its walls takes expert skills.
Vale, centra més el panell, que hem d'anar més cap allà. Vale, i sí, segueix manant el José. Quince, 10, sigue, sigue José, sigue, y quieto. Well.
The first panel fits, and the bolts slide into place.
This is the real proof that the system is a very good system. This piece is here forever. Forever. Well.
But the build team can't rest. They want to install the entire level, 8 panels, before nightfall. But just as they start to lower the second piece down into place,
Vale, José, seguimos bajando.
They hit a problem. This set of bolt holes doesn't line up.
We don't know why, and now we need effort a bit more. All the team working hard.
This monumental build hangs in the balance.
We only need a 10th part of 1 mil. Less than my head.
They use clamps and wrenches to wrangle the panel into place. Some extra muscle power finally forces the bolt holes into line.
We have need a bit more time, but at the end, this is in its correct place. Breathe deep and try again. This is the result. Happy.
Jaume's crew pushes hard to install the remaining 6 panels that make up this tower's first level.
We are going to take them and we want to lift up quickly.
Their innovative prefabricated panel building technique seems to be working. It takes the full day to slot all 8 panels that make up the tower's first level into position.
We learn every day another new system, another new technology.
Completing work on the towers will take almost 6,500 tons of stone. Emma's team at the Lancashire Quarry has their work cut out to keep supplies rolling so construction can stay on track.
We cannot keep up with the demand from Barcelona. As fast as we can produce, they're using it.
The quantity is
is good.
A geologist from Sagrada Familia makes regular visits to check the quality of the stone is consistent.
It is a critical job because the towers have to be structurally strong, and this stone is the only stone that they found to match the original.
The quality of the stone is perfect.
Once each batch is signed off, some of it is delivered to these expert craftsmen in Barcelona. They shape each piece based on the team's study of Gaudi's models and sketches.
When you are working with the stone, it's like a connection. You speak with it and it speaks with you.
Galician stonemasons Emilio and Alessandro are sculpting flowers, leaves and letters that will form part of one relief for the tower exterior.
It's a very big job. To do all these stones by hand will take half a year, yes? If I have to do all by hand.
To speed up the operation, highly specialized robots form the rough outlines of the flowers and petals.
Robots never make mistakes. Very precise and very quick, and cut the stone like butter. Robots never take a siesta, so they are always working, and Sagrada Familia needs a lot of stone and needs very quickly.
But robots can't replace the dexterity of the human hand. Once cut, it's down to Emilio and Alessandro to turn the inanimate into art.
The robots, they don't have feel. And we bring the stone alive. We bring the stone alive, working by hand.
Smooth surfaces on the leaves and petals make them look closer. Deeper, harder chisel strikes give the impression of distance and depth.
It's like magic, no? The 3 dimension.
With the help of the robots, Emilio and Alessandro inch closer to completing the complex stone relief. During the tower design phase, engineers faced another critical challenge. They had to be sure that the towers would be earthquake-proof. Europe has 1,100 geological fault lines that trigger up to 300 earthquakes every year. The taller the towers rise, the more vulnerable they become to tremors that might strike the region. Forces pushing from the sides of the towers, like earthquakes, could cause the panels to collapse.
Any lateral forces like wind or earthquakes will make these blocks fall easily.
Pau's team need to squeeze the blocks in each panel together to increase the rigidity of the towers.
So if we put the blocks in compression, we can avoid that these blocks collapse with the wind loads or the earthquakes. And then this is stable. There's no way this can fall.
The easiest way to compress the stones in each panel would be to wrap them in steel cables. But this would ruin the look of the towers. They must look like stone from the outside. Another option would be to brace the towers from the inside, building a supporting frame of steelwork. But this would block up the space needed for the spiral staircases.
You can connect to the steel columns to hold the panel up.
With help from a team of British engineers, the architects devise an ingenious solution that won't compromise Gaudi's design.
So when we have earthquakes, this steelwork gives us the ability to bend elements and absorb energy.
Their solution is to incorporate a secret steel skeleton inside the tower's stone. Sets of steel tendons will run through each panel. Tightening these tendons will lock the stones together. Once locked into the hidden steel frame, the towers look like solid stone. They can now resist almost any lateral forces, such as high winds or earthquakes. That's the theory. Now they must put it into practice.
We're gonna begin production, and it's time to see in reality how does it work.
At the prefabrication yard just outside Barcelona, Jaume's team must thread these stainless steel tendons down through the next batch of tower panels. Workers use hydraulic jacks to press the blocks together to form a solid unit.
After the press, all the 16 stones that they are in this panel is only one piece.
As the jacks squeeze the panel tight, the team tighten the nuts at the ends of the steel bars running through the blocks, locking them in place. On site in Barcelona, the next batch of earthquake-proof panels has arrived. Now, Jaume's team must begin building the larger tower at the rear of the temple. Each of these panels weighs 10 tons, 3 tons more than the panels of the smaller towers. That's a lot of extra weight to keep under control.
The enemy today for us is the wind. A strong wind can take down the crane.
Heavy onshore winds blast the city, and gusts at the top of the basilica are far stronger than at ground level.
At the moment, the wind is correct and we are going to start.
Crane driver Jose scales the 460-foot high tower crane. Not a job for the faint-hearted. If the wind catches the 10-ton panel, it could act like a sail, swinging wildly out of control, smashing into the basilica.
Imagine if the piece would fail with 100 meters high, it would be really horrible.
Posible, 58.
It takes a steady hand to guide the first 2 panels into place as the wind slowly picks up. As the gusts hit 37 miles per hour, Jaume gets some bad news. The winds are too strong to install the panels.
We can lift. It's impossible. I don't make the lift. The wind is growing up minute by minute. I don't know. We have to wait.
The following day, the gusts die down,
Vale, José, puedes ir bajando.
and Jaume can continue to push the towers skywards.
We need the best weather conditions.
Touchdown. And with its steel tendons secured, this piece of Gaudi's sky-high jigsaw should be able to take a pounding from the winds and earthquakes for centuries to come. As the 6 central towers continue to rise, another team is hard at work, making the ornate stained glass that will sit inside some of the windows. The church's visionary architect, Gaudi, left barely any instructions for the stained glass. So it's down to glass artist Joan Vilagrau to devise a design Gaudi would approve of. He's worked on this giant glass puzzle for the last 18 years and is passing his skills down to his son, Tony.
Molts anys pit, que és aquest que estic treballant. My grandfather was painter. My father was a painter. I am a painter. Tony is working too in paintings. I couldn't imagine that the effect of the colors could be so deep in the people visiting the Sagrada Familia.
The nave of Sagrada Familia, completed in 2010, showcases some of the 17,900 square feet of stained glass contained within the basilica. The light streaming through colors the pillars and walls.
I walked in and it was like goosebumps. Just so completely blown away by the light, the color, the structures.
Choosing what colors will be in one side and another was to create a kind of mystic ambience.
In the morning, the sun shines through the east side of the nave, bathing the basilica in blue light. In the evening, the space turns red as the west side illuminates.
It's the normal changing of the colors during the day. The constant discovery of new effects of the light depending on the hour of a day.
Workers use traditional stained glass techniques to realize Joan's designs.
The techniques in the production of glasses are totally the same in the Middle Age. The way to make the glass have changed a little.
Finally, Joan and Tony's beautiful windows can be installed in the towers. Outside, the team is picking up the pace erecting the church's towers.
Vale, José, sigue subiendo.
This new stonework will add an extra 6,500 tons of weight to the roof. That's almost as much as the Eiffel Tower on top of the building.
Will be extraordinary. When the towers will be finished, the image of the Sagrada Familia will change.
Supporting this immense weight creates a huge challenge. The builders of traditional Gothic churches found an ingenious solution to support their towers. This is Cologne Cathedral, which took a staggering 632 years to complete. It's currently the world's tallest twin-spired church, soaring 515 feet high. The incredible structure was made possible by using flying buttress technology, huge stone arches that prop up the cathedral walls. The buttresses transfer the weight of all the stone down into the ground and stop the structure from collapsing. When complete, Sagrada Familia will soar 50 feet taller than Cologne Cathedral. Its pioneering engineers needed to find a way to support the towers, but they faced a conundrum. Gaudi hated flying buttresses. He considered them to be ugly, unnatural crutches.
We need support them. But this is not only a question of weight. Also is a question of forum.
The arching effect of flying buttresses would have transferred the weight above down into the ground. But the buttresses would have blocked the light streaming through the stained glass windows and ruined the effect of the facades. So Gaudi moved the arches inside the basilica and supported them with 56 massive columns. Ahead of the curve and almost 100 years before the tower build began, Gaudi had found a way to channel their weight down into the ground and free Sagrada Familia from the flying buttresses.
No buttresses. The columns will support the towers. All the elements that you look in the Eiffel of the Sagrada Familia have a structural function. It's extraordinary. It's a very ingenious.
The 4 columns taking the heaviest load beneath the main tower are made of red Iranian porphyry, one of the strongest stones in the world.
The architecture of Gaudi is an architecture of the synthesis of a structure and of the forms, and the result is the beauty.
Thanks to Gaudi's forward-thinking design, when topped out, the world's tallest church towers will have all the support they need. Finally, after 135 years, an estimated £900 million, and a whole lot of engineering ingenuity, workers here have decoded the maverick and mysterious vision of Gaudi.
It's a big honor and a big responsibility to feel you are part of a history developing this project.
It's not simple, but I'm sure that my generation can see the Basilica finished.
The team is well on their way to finishing Sagrada Familia's massive crowning towers, to finally complete this extraordinary structure in time for the centenary of Gaudi's death.
The tower is growing to the top.
If Gaudi look this tower, perhaps he's looking. I think Gaudi will realize his project in the construction. I feel that we are continuing history.
Known as God's architect, Gaudi is famed to have said, "My client is in no hurry." But it won't be long before Sagrada Familia is complete, and Gaudi's client will have the world's tallest church. Today in New York, this team of engineers is attempting to build a remarkable superstructure.
We change the skyline every day.
One of the world's most luxurious skyscrapers, right in the heart of busy Midtown Manhattan.
We're building a skyscraper on a postage stamp.
71, you got it!
Up, up, up.
Constructed with an innovative steel and concrete frame,
Come to daddy.
and soaring over 1,000 feet above this bustling metropolis, this unique building will even house a museum in its base.
We build everything by hand, one bar at a time.
All stop.
It's like you're building a small city.
To construct this titanic 82-story high tower, the team must battle extreme heights.
You have fear for heights. This is not a job for you.
Nice and easy.
Over gridlock busy streets.
We are in Manhattan. People are getting crazy.
So this thing is way off. We are building part of history.
This skyscraper ranks in a league of ambitious new engineering wonders that are bigger, faster, taller, and more advanced than anything ever constructed before. This series charts the inside story of the extraordinary race to build these giants. New York, America's biggest and busiest city, and the testing ground of one of the world's most extraordinary modern marvels, the skyscraper. Over the past century, engineers in this city have built some of the most inventive and iconic towers on the planet. From the pioneering Flatiron Building to the geometrically complex Hearst Tower. In the 20th century, building a skyscraper was all about how high you could go. But today, in this crammed city, the challenge is simply finding a spot to put one. In 2007, this small plot of land became available next to the city's renowned Museum of Modern Art. At just 17,000 square feet, in most parts of the world, it might just be big enough for a car park.
There's a suggestion to put the hoist on the south side.
But this team, led by developer Tim Flynn, is attempting to build a pioneering skyscraper on it.
Spreading out horizontally doesn't work, so we have to go vertically to the sky.
Building anything in the heart of bustling Manhattan is a huge challenge.
I'm sure anyone who's built a large project in a congested urban setting can tell you that space is a premium. This project right here sort of takes that concept to the next level. We're building a skyscraper on a postage stamp.
This is the striking concept for the skyscraper that Tim must build. Its lower floors will provide an additional 50,000 square feet of gallery space for the Museum of Modern Art. Above this, the tower will house 146 ultra-luxury apartments, a gym, spa, wine vaults, and a restaurant. Workers must erect a sturdy frame around the building to form its skeleton. The tower's 1,050-foot-high walls will change angles 13 times as it rises. This gives each floor a unique shape that tapers to 3 sharp points. Apartments above the 46th floor will enjoy the ultimate luxury: unbroken views of New York's iconic Central Park. The tower is called 53 West 53rd, after the bustling Manhattan street it sits on. But building it here will push Tim and the team to their limit.
Our building takes up the entire footprint of our site. On the west side, we've got a high-rise commercial office tower right against the site. On the east side, we've got one of the busiest museums in the world. On 53rd Street, we've got a subway tunnel right underneath our feet. So we've got 2 subway tubes immediately adjacent to the site. You have to deal with it. The buildings are going to get built. We just have to figure out how exactly to do it.
This is their plan. First, they must excavate the foundations for the tower. They must drill 33 concrete pillars up to 70 feet deep into the bedrock, avoiding the subway beneath. They'll build each floor with wooden molds, then fill the molds with colossal amounts of steel and concrete to form the strongest possible structure, 1 floor every 5 days. Halfway up the tower, they must build 3 gigantic support floors. These will tie the rigid core of the tower to the exterior walls and help them stand up to strong winds. They must install over 5,000 panels of aluminium and glass to create the tower's skin, mimicking the shape of its sloping columns. Workers will top the tower off with 5 glass and steel pyramids to complete 53 West 53rds iconic look.
We've got a big challenge ahead of us, but we feel we'll stay ahead of it.
The first step is to install a crane to piece together the tower's frame. They can't park the crane on the busy street, so they must assemble it right in the middle of the site. With the crane in place, the lower floors begin to rise around it. Tim's team has just 55 months to build and fit out the tower so residents can move in on time. There's no room for delays.
Schedule is everything. We're running a business here.
It takes 2 years to build just the first 30 floors. Now, as the tower rises taller and starts to taper, closing in on itself, the real challenges begin. Traditional skyscrapers are held up by dozens of internal columns. These run through the building and leave the exterior walls free to be clad entirely with glass. But this tower has a tiny footprint and narrows towards its peak. Floor space is precious, and support columns would eat it up. So this is their innovative plan. To maximize the floor space, the tower's architects have taken the bold decision not to use internal columns. Instead, they'll direct much of the structural support into a steel and concrete exterior frame called a diagrid, the largest of its type ever attempted. Knitting all this steel together has been a problem for the tower's consulting engineers, Steve Bongiorno and Jamie Silva.
The problem is when you converge to a joint, now you have individual reinforcing bars that need to kind of connect and consolidate into a joint.
If you were to reinforce one of those joints with the standard rebar, you would have very little room.
Steve and Jamie plan to reinforce each diagrid junction with a precise amount of steel. If 3 or more diagrids overlap, the steelwork required simply won't fit inside the building. To solve this, they've designed a clever junction called a node. They are huge slabs of 3-inch thick steel covered with precisely angled sockets, loaded with super high-strength steel bars. The steel bars must be the exact length and angle to slot into the structure's steel skeleton. If any bar doesn't align perfectly, the node won't fit and the tower won't be strong enough. But with 31 perfectly designed nodes, every part of 53 West 53rd's exterior frame should channel the weight of the building to the foundations. Expert welders are fabricating the nodes at this workshop 20 miles northwest of Manhattan in New Jersey. It's taken months of work to craft these specially designed nodes with a perfect combination of strength and precision.
You're looking at what's really holding up this building right here, in this amount of space. This is the first time this has been done in a concrete building. By using these nodes in the diagrid, we're able to safely channel the loads coming down through the building and into the foundation.
It would be impossible to build this tower without these nodes. But if the nodes don't fit together, it's back to the drawing board.
This is basically one of these square connectors loose. And the bars connect into these connections. When you get out there, these 6 bars have to match up pretty much exactly with 6 bars coming up out of the concrete. Accuracy and precision is paramount to having these connections work.
How we doing? Good, good. Right now, we can't go any higher until those nodes go in place.
This floor is a big test for the experimental nodes.
We don't have nodes on every floor. This floor happens to have 3. So it's critical that they fit in place. If something went wrong and we can't fit it in, that's just delaying the progress of the deck.
Hey, Tom, Steve, have you seen Devin yet?
Steve Bongiorno is on site to make sure his nodes slot into place.
The heavier one today is about 13,000 pounds, 6.5 tons.
Keep coming down.
John Renner provides Steve's eyes on the ground.
It's all about the angle to get them inside the column. All these columns come on different angles. It won't fit unless it's connected the right way. All right, Nick, easy up on the line.
This node weighs 6,000 pounds. It's far too heavy to wrangle once in the air. They must raise it at just the right angle so it slots in snug first time.
You got about 4 or 5 feet of slack. Keep coming left, Nick. 2, 1, up, 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 Nicky. Up, 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 take it, Nicky, all you.
This is the crucial moment they find out if the nodes work, and if this pioneering way to strengthen a skyscraper can succeed.
You can see it there flying in the air.
Its 10 steel bars must land precisely into connectors up top. But just as they approach the drop zone,
actually, now that I'm looking down there, this thing is way off.
they hit a glitch.
Something doesn't look right. I'm worried about the bottom. Oh, one of them's not gonna be able to go.
None of the steel bars line up in the right position.
This bar can't go anymore. It's hitting something up there. That's a major problem. It's a major problem. Once he welds that on, how are they going to get it down there?
I gotta come over for this one. Hold on 1 second, Rich.
I don't know how they're going to get this in. It's a foot longer than it should be. And we don't have that kind of adjustment.
Yeah. I got one.
Not easy building any building. A building like this, it's extra hard. This one we should be able to go up a little bit. Is it going to be enough?
2 steel reinforcing bars are too long, which means the crucial node that holds the frame of the skyscraper together won't slot into place.
This was a problem of our making. We're supposed to get a final survey at this point, but that survey information never got back to the computer. Everything was done to the right length. It's just starting from a point that was higher than it was supposed to be.
If they can't get all 6 bars on this node to fit into these connector joints, construction work may have to shut down, setting the entire project back months.
These 2 on the bottom, this is being restricted too, right? You're gonna have to start putting those in.
If we connect this one and this one, all you're gonna have is 5 inches. You need 12 to go down.
So these 2 bars, the 2 bars on the backside were installed a little too long. We're gonna have to cut the bar. Because I don't think there's any choice but to cut the bar. So this will be a first. All right, anybody see any other way to do this?
Months of precision engineering have gone into making this node. Cutting the bars on site is a high-risk strategy.
9 foot 2.5.
If they cut too much out or damage the node, it will take months to build a replacement.
There's really no solution here except to cut about 8 inches off of those 2 bars. It's always something different, too.
While Steve's crew remove the node and fire up the saw,
2 or 3 feet up, all right? Nice and easy.
on the ground, John is anxious to make headway installing the next node.
This one is 13,000 pounds. The other one was 6,000.
It's twice as heavy, so twice as hard to wrangle into position.
What if we lean it, put it around over here? Maybe try and lean it this way, the way it is?
They need to angle it at exactly 84.3 degrees before they lift it up, so it slots into its connectors.
Easy down now, Nicky. Easy down. Coming up, brother. It's got to be more horizontal. It's too much of an angle. If you see the sackle up top is on an angle, it won't fit into the hole. So all that weight is on their nozzle now.
Up top, the team has chopped 8 inches off the bars on the first node. Now the big test. Will it fit?
This looks good. This is now secure enough to release the crane, and they'll have to, obviously make the other 4 connections. But at that point, the crane will be gone. We'll be on to the next one.
Steve's quick fix saves the day. Now they must psych up to battle the heavy weight below.
Third time's not a charm. I'm heading to Mexico.
All good. Got the right angle. Up, up, up.
It's a nerve-wracking wait to see if all 12 bars on this monster node are the right length to slot into their connectors.
Beautiful thing. Yeah, you got it, Richie. You can start calling to me as we go lower. Yeah, here you go. Good. Oh, hold it.
This time, it's a perfect fit.
Even the bars are lining up better on this one. This is a good sign. So we're gonna get out of here before it gets dark today.
All right.
Now the team just have to tighten the nuts.
Thanks, guys. You did a great job. That's how it's supposed to be done.
And the critical connectors for floor 31 are in place.
This is ready to go. It's a long day, but it's worth it. We're above the halfway point, and we're charging up the building.
The team takes a well-earned break.
My first job was on the Empire State Building with my father in 1987. We were working on the antenna together. Back in the days when my father was working, they didn't wear harnesses. They didn't wear safety gear, nothing. Glasses, gloves. My father was in the hospital every day taking metal out of his eye. Almost every week, really. He never stopped. It's changed a lot. I'd say 80% of the iron workers, their sons are iron workers. I think that's part of construction. You know, the honorability, the camaraderie that comes with the men. You grow up wanting that. And we're like a brotherhood. These are all my brothers here. I come to work, I feel like I'm with my family, hanging out, enjoying our day. Couldn't do it without them.
Over the next few months, Steve's team picks up the pace. The Skyscrapers' show-stopping angular frame starts to take shape. Step by step, they're getting closer to this. This is what the tower's ultra-luxurious apartments will look like when complete. They are being designed by world-renowned interior architect Thierry Despont.
I restored the Statue of Liberty early on when I came to New York, which for a young French architect was a pretty exciting project.
The Skyscraper's unusual diagrid frame makes designing its apartments a unique challenge. To help grasp the scale of this task, Thierry has built this full-size mock-up, engineering this apartment around the imposing diagrid columns.
As you can imagine, those columns is going to be different on every floor. You can obviously simulate it on computer, but it doesn't translate as well as actually seeing the space.
With every apartment's layout squeezed around a different section of the constantly changing tower, the challenge is to maximize floor space without losing the high-end feel.
Here, literally, we designed 146 some apartments. They're all different.
The team can't build these interiors yet. Tim's making headway past the 33rd floor, but something has put a huge hole in his schedule.
We're looking at the tower crane right now, and on a small site, starting from ground, we have to have that tower crane within the footprint of the building. We're right now on the 20th floor, and you see this is coming down from bedrock and coming up. We've left slab openings for 20 floors now.
There's no space on the sidewalk outside the building, so the crane runs up through the center of the site. This leaves a gaping hole in every floor, from floor 1 right up to floor 32.
When you have a massive hole in the floor and a tower in the middle of your building, it really limits your productivity on each floor.
Tim's team needs to fill in these holes so it can start work on the interiors. To do this, he's come up with an ingenious solution.
What we're doing is we're putting a platform hanging off the side of the building above the activity of the street, and we'll install a second tower crane on that platform, which will be outside of the building, which will rise with the building 1,000 feet in the air.
In another engineering innovation, they will construct a new crane on this temporary steel platform outside the building that scarily overhangs the street like a diving board.
We've got a team of ironworkers doing the last part of the installation of this diving board. And they're getting ready to start stacking tower sections for the crane on top of this.
The team teeters on the edge of the platform to guide the 13-foot-high crane sections into place. This isn't a job for the faint-hearted.
Just the way it is, counterclockwise.
It's a high-rise spectacle for the neighbors.
All right, about a foot over the pockets. Come on down easy, get you started. Keep coming. Another foot. 8 inches. And all stop.
With the first piece set, the team race to assemble the rest of the crane. Like one giant Meccano set. It takes dozens of bolts to lock the sections together and hold the 450-ton crane steady. This new crane will help the team scale even greater heights, right to the tower's peak, but without leaving a massive hole in each floor.
This is one of the major milestones. We get the second crane operational and the first crane removed from the building.
It's now a frantic race to fill in the holes left by the old crane with toughened steel and concrete to make a seamless join. But as the tower soars into the sky, it becomes vulnerable to the elements.
Wind is a particular issue here. We're going to be up above all these other buildings and taking increased wind forces, which is causing a building to want to overturn.
The Atlantic Ocean drives ferocious storms and deadly hurricanes right into the heart of New York. Manhattan's skyscrapers bear the full brunt of these gusts, especially at the top, where winds can be many times stronger than those at street level. How can Tim's team protect this 1,050-foot-high tower from these forces of nature? A rigid core of high-strength concrete and steel runs right up through the skyscraper to support it inside, while the network of diagrids holds up the exterior. But these innovations are not enough to stop extreme winds damaging the structure. So Tim's team has designed an innovative web of 2-foot-thick concrete walls that must be built between the 35th and 37th floors. They call this structure an outrigger. The idea is for the outrigger to tie the core to the diagrid and stiffen the building by over 15%. These walls take up so much space that it's impossible to squeeze apartments into this zone. So this is where they plan to pack the skyscraper's air conditioning and plumbing equipment.
So these are very important structural floors. These outriggers that are going in both directions, tying them together. So we have massive 2 feet thick walls with a tremendous amount of reinforcing steel.
But just as they gear up to start pouring the massive concrete outrigger walls, the weather turns.
I'm standing here in the rain and there's nobody standing around me working. We normally have 150 men and women working like bees around this area at this time of the day.
The rain will dilute any wet concrete and weaken the outrigger walls. Whilst the rain keeps coming, no one can build this tower higher. But not everyone has been forced to down tools. Down on the 22nd floor, this team is pushing on through the bad weather.
This is going to be a good condo. Yeah, this is someone very special is going to be living here.
Mark Skorowicz heads up a team of master carpenters.
Me, Patrick, and Vinny, we work on the columns.
Mark's team create flat-pack wooden molds called formwork. These surround the steel of the diagrids. Workers then fill the gap between the steel and formwork with concrete to finish each column.
You build it, a box. It encases the rebar, then you can pour the concrete in. And then after the concrete cures, you have a column. They're all labeled for the direction that they're facing, the height of the floor, where locations, north, south, east, west. And the guys upstairs, they can put it together. Time is money in the concrete business. They want to get it done yesterday, you know? We've been working together for a long time. Half of us known each other for 10, 17 years. We take care of each other like a family. I always envied the guys that were, up there hanging off the buildings when I was younger. And that's what I wanted to do, and I'm here.
Mark and the carpenters make headway with their wooden formwork. But no one can pour any concrete into it until the rain stops. The next day, the skies are clear. The team arrives early and gets ready to finally pour the concrete to build the crucial outrigger floors.
It's a beautiful day up here. It's breezy, it's a nice day to work. It's a perfect day for concrete today.
But getting 5,000 tons of concrete to this site is no simple task. There are no concrete plants in Manhattan. The biggest lies 13 miles away, across New York's East River, deep in the borough of Queens. Tim needs to guide over 250 trucks across Queens, through tunnels under the river into Manhattan, up 3rd Avenue, and then across town to reach the construction site. In New York, a journey like this can take hours in heavy traffic. The concrete has a lifespan of just 90 minutes before it becomes unusable. From the moment it hits the truck, the clock is ticking.
All right, 71, you got it.
It's going to take some superhuman driving to deliver this load through the morning rush hour. Kurt Reinecke leads the charge.
Yeah, you want to be there in less than 90 minutes. We have about an hour and a half to get to the job. We've already used 20 minutes of that time getting to this point, so we're going to be cutting it close. It doesn't look good. It's flowing, but we're only doing 4.
At 4 miles per hour, it will take Kurt more than 3 hours to reach the site. The concrete will have set solid. As Kurt crawls through the Midtown Tunnel, the team on site lose precious time.
We are in Manhattan, and here we go. People are getting crazy already. We're slower than walking right now. We are slower than walking. We're at 54 minutes now. It's almost an hour. It's going to take us at least 15, 20 minutes to get across town, so we're still cutting it close.
The closer Kurt gets to the skyscraper, the denser the traffic becomes.
Come on, you could hit the gas. It's the one on the right. Oh, this guy is here for us.
He makes it, but the concrete is at the limit of its usable life. Tim's team now has a razor-tight window to lay this load before it's set solid. Huge pumps suck the concrete to vast pouring machines on the 35th floor. They must make sure that the concrete pours into every nook and crevice of the outrigger and formwork. Any gaps or bubbles could weaken the finish. With work on the outrigger floors well underway,
it's impressive. It's getting there.
Gary Pomerantz can start to install the tower's crucial utilities inside the outrigger. It's electricity, plumbing, air conditioning, and most critically, water.
The toughest thing in residential is the morning peak. Everyone gets up, everyone takes showers, everyone's got kitchen sinks on, and what is the right amount of water and what is the right amount of, more important, hot water to have available? And there's science and there's know-how.
Residents in this tower will consume around 22 million gallons of water every year. But pumping water up a skyscraper is a formidable challenge. The pressure in the pipes beneath New York is only strong enough to push water naturally to the 5th story of a building.
The majority of New Yorkers who live in tall buildings have wood tanks on the roof. We're filling them all day long, and we drain them down.
The wooden water towers perched on rooftops across the city are more than technological relics. They are the primary source of water for many New Yorkers.
It's a New York thing. Every city's got their thing, and that's one of them for New York, and it's kind of cool. And this building footprint is the challenge. The floor plates are tiny. The round water towers, they take up more space because it doesn't fill the corners. If you imagine a cylinder inside of a square.
A single massive water tank at the top of this narrow building would fill the penthouse suite. So Gary has developed an innovative solution. He has divided the skyscraper into 2 zones. Pumps in the basement push water up to the 37th floor, where it is stored in 2 rectangular concrete tanks, each holding 3,500 gallons. From here, a second set of pumps pushes water to another pair of tanks at the top of the building. When residents in an apartment turn on a tap or the shower, water flows back down under its own weight.
The water gets up to the top in stages, and there isn't one single pump that does all the lift, and there's not a single piece of piping or equipment that sees the full pressure of the system.
Gary will squeeze his vast concrete water tanks into the outrigger floors.
This is where the water tank's gonna go. From here, down through here, and it'll be filled with water.
It's a new solution to an old New York problem. With the crucial outrigger floors nearly complete, 53 West 53rd soars up towards its final height of 1,050 feet.
So we're 45 floors up. We've got about another 35 floors to go after this.
Good, Robbie.
We're pouring a floor every 4 days, and we're starting to really see those views that we were looking for. We can look to the south and start to see over Rockefeller Center all the way down to the World Trade Center. We can see Tower number 1 standing up proud down there. If we look to the north, we've got full views of the Central Park.
His team must complete one final challenge. They must clad the tower's unique diagrid frame in a top-to-toe glass skin.
This is the structural, the bones of the building right here. But our architect has chosen to express the structure on the exterior of the building.
The design of the skyscraper's glass exterior was inspired by one of the earliest and most iconic skyscrapers built in New York. The Flatiron Building was constructed in 1902 on a small triangular plot of land. The skyscraper appears to be made from stone. But to build a tower this tall from stone, its walls would have had to be so thick that there would be no space for rooms inside. Its designers came up with a groundbreaking solution. Under its skin, they erected a frame of steel columns and beams to hold up the building. The stone and terracotta exterior is nothing more than a thin facade, called a curtain wall, that hangs from the frame just like a curtain. It keeps the weather out and gives the skyscraper its iconic look. 115 years on, Tim's team is using the same idea. They'll wrap a curtain wall, made from aluminium and glass, around the building's diagrid frame.
That is the architect's concept, his vision, to see the structure expressed on the curtain wall. So when you look up, you see the diagrid patterns crisscrossing up and throughout the building.
Here's the plan. The curtain wall will cover all of the diagrids and contain all the glass that makes up the tower's windows. The team must install over 5,000 separate panels to cloak the entire skyscraper. Each panel contains the exact amount of aluminium to cover the diagrid and glass to form the windows. They must hang each panel from the floor slab of the building. Special connectors lock them into place. The panels clip together to form a curtain wall that conceals the inner structure.
Push this one forward, pull this one over here.
The challenge with this particular building, that every floor is different. We're sloping back on all sides, and we get smaller and smaller as we go rising. The layout's different on the next floor, the concrete's different, the curtain wall's different, everything's different. The pressure is on these guys.
That's good, that's perfect, leave it right here.
Frank Mahoney leads the team attaching the wall to the upper floors.
So a big challenge. It's not like a basic circle building all the way around. There's a lot of strategic angles. It's not as easy as a normal building. This side marries into this side, and they interlock with one another. Like a Lego system, it locks right in, beautifully. Hold that. You have fear for heights. This is not a job for you. 100%. All right, calm down. Calm down.
Frank's team must work right on the edge of the building.
I got it.
To slot each panel into place. Special connectors tie each panel into the structure to make a watertight seal.
Your gaskets are right here, prevents it from leaking. So they're all racked, plumbed, caulked, and sealed. Right now, these are all ready, these are all finished. We're looking great. Beautiful.
Over the next few weeks, the team hit a good rhythm, and the curtain wall starts to take shape. The higher they get, the harder it becomes.
Over here, we have plenty of room, you know, open space. You got tons of guys that can move here, move there. You operate from all kinds of areas. But you come to a point where it marries into the building and there's no other floors.
The skyscraper is formed of 5 pyramid shapes. These narrow towards the top of the tower and join together. These zones are called apexes. The shape and height of each apex makes them extremely difficult to clad with the glass curtain wall.
There's no way for us to really get up and work in there safely.
And the apex is a very small place. You have to do it from above.
Keep it coming back. You got him.
Frank's team tops each apex with a massive sheet of curtain wall.
Here we go. Keep them coming.
Almost 5 times heavier and 3 times wider than most panels.
Straighten it out.
Lifting something this large and fragile high above the streets of Manhattan is precarious work. The team must stop the traffic and clear the streets.
Here we go. Keep it right, keep it right. Good job, man. Awesome.
You drop the tape measure from this distance, a little tape measure, you kill somebody. You drop a 2,000-pound unit, you're killing people.
Frank can't allow anyone to step underneath this heavy panel until it's close to the drop zone.
You can't be under any load for safety, just in case something goes wrong. A choker could break, anything could happen when the load comes down.
As the first apex closes in, the team squeezes out onto the 3-foot ledge to guide it into position.
It's about a 3-foot hole to sneak through, get in there, to go through, to make the final little adjustments, just to land it onto the anchors. Just watch that scalpel for me, Tony, okay?
Touchdown must be perfectly aligned for the building to achieve its signature look.
We don't put it in right, it don't look right. It's the face, you know? It's the covering. It's like a nice jacket.
All right, let's get it closer.
All right, we're touching. All right, we gotta go tight to the wall.
The team must muscle it into place.
All right, I got about 7 inches. Which way, up or down?
It's just gonna come down. He's probably 2 inches high.
It's coming. It's gonna come. There you go. There you go.
You're looking pretty good right there.
And it's locked in. With one of the tower's apexes in place, the team has proved they can build this giant.
It's a first for me. I've never done anything like that before. Anytime you do something new, it comes with its own set of new problems to figure out.
It's a big milestone for us today. We got the apex in successfully. We've proved that it's possible. We feel we've got the hard part done.
We can move on and we can stack on top. And then everything else from there is, it's not gravy, but it's almost like grandma's meatballs and gravy.
And now the final craftsmen begin working, fitting out the apartments. These are the finishing touches to a construction job that has pushed the team to the limit.
We knew that this building was going to be an incredible challenge. We all have to come together and perform at our best to execute a project like this. And that's what they're doing every day.
In a few short months, once the exterior of the tower is complete, this 1,050-foot high building will be the most radical and elegant skyscraper on New York's skyline.
Everyone who worked on this team will be looking at this building every time they see it and say, boy, look what I did. Everybody that's involved, and that's a wonderful feeling.
I gotta tell you, it's been overwhelming. I'll be telling my grandchildren I built this place.
In the Arctic Circle, this team of elite engineers is embarking on an epic endeavor.
It's a very, very big operation.
In just 5 years, they're attempting to construct a remarkable new superstructure. The longest suspension bridge ever built in the Arctic Circle.
We have only one chance to build this bridge.
Constructed from more than 11,100 miles of steel cable and soaring over 580 feet into the clouds. The team must battle extreme heights.
They need to be very, very careful when lifting.
And surging 80 miles per hour winds. To complete this 5,029-foot-long bridge before the winter weather strikes.
The weather can be extremely tough.
It's a dramatic situation. Actually, we're quite scared.
This groundbreaking bridge ranks in a league of ambitious new engineering wonders that are bigger, faster, taller, and more advanced than anything ever constructed before. This series charts the inside story of the extraordinary challenge of building these giants. northern Norway, deep in the Arctic Circle. In this part of the world, icy mountains soar high into the clouds and plunge deep into the freezing waters of the Norwegian fjords. The remote industrial city of Narvik, a crucial hub for fishing and mining iron ore, sits to the south of the giant Rombak Fjord and has a population of around 14,000. But the stunning landscape here also creates a problem for residents: a killer commute. To access the north, they must drive a treacherous winding road, 11 miles around the edge of the fjord. Rockfalls and landslides often kill and injure motorists along this route.
The road around the fjord is very dangerous in the winter.
This road is not so easy to drive. There have been a lot of crash on this road.
So to save lives and cut commute times, engineers are planning to build an ambitious new crossing over the water, called the Hålogaland Bridge.
This green line indicates where we are building a new bridge, and it means that we will have a much more safe road, a shorter way, and we don't have to use this old one that is exposed for rock slides.
Conceiving its design rests on the shoulders of structural engineer Jamal Assad. It must be able to span the 980-foot deep fjord and still survive the bitterly cold environment.
The bridge will improve the whole infrastructure in this region. I've been working on this bridge for almost 10 years to create something unique, not just for this area, but also around the world.
This is the giant Jamal and the team must somehow construct. Twin A-shaped towers, built from over 42,000 tons of concrete, will rise from the bottom of the fjord. Two huge cables will hang between the towers. Each cable weighs 2,000 tons and measures more than 1.5 foot thick. The cables must hold up a custom-made, dual-lane road deck, made up of 30 steel sections. Each cable will be anchored over 150 feet deep into the heart of the mountains on either side of the fjord, to hold the bridge steady through the roughest weather. Stretching almost 1 mile across the water and costing £332 million, the giant Hålogaland Bridge will be the longest suspension bridge within the Arctic Circle. But the northern location makes building this bridge extra tough. The Arctic environment is brutal. Temperatures here can drop below -15 Celsius, and 80 miles per hour winds race between the mountains.
Bad weather can cost a lot of money.
If not built right, the results could be catastrophic. Suspension bridges are extra susceptible to the force of the wind, making the construction of this bridge an extraordinary challenge.
You can see that all these hills give a climate which will be challenging to construct a bridge.
Yes, so that's one of the things that we have to clarify.
Building this one-of-a-kind bridge in such a uniquely hostile location involves a series of complex stages. On top of 4 huge pillars, the team plan to build up the massive A-shaped concrete towers. Then they'll carefully winch 80 wire strands 566 feet up and across the freezing fjord. These will form the 2 colossal main cables. Next, they will jack the 2,000-ton cables apart by 51 feet in the center of the span and attach 110 steel clamps and vertical hanger cables. These will hold up the 30 aerodynamic steel sections that will form the 7,000-ton road deck. Finally, workers must race the winter weather to lift each section of deck into place to create almost 1 mile of roadway between the towers. For Jamal and project manager Dagron Kassen, it's going to be a real battle against the elements.
think it's quite a challenge to build bridges in this part of the world. We have the dark time of the year. We do have all kinds of weather.
Dagrun heads up a team of 900 engineers and workers from Norway and across the world. None of them has ever attempted a bridge on this scale in such a remote part of the world before.
So challenging, but altogether we have an amazing team. And we will make it happen.
Dagrun's first challenge: construct the bridge's giant reinforced concrete towers. Building work begins in 2013. King of concrete, Guttorm Reidar, must erect the towers at high speed. To do this, he uses an ingenious technique called slip forming.
You can reach about 2.5 to 3 meters each day, and you work 24 hours a day.
Workers fill a special mobile mold that clamps around the leg of the tower with concrete. Once each layer of concrete is set, hydraulic jacks raise the mold up to the next level, so the towers continue to grow 8 inches at a time.
You constantly pour concrete, and when the concrete are cured enough, you lift the slip form a little bit to you have enough space to pour new concrete on the top.
The team pour the concrete non-stop, 24 hours a day for an entire week. Over 32 months, they raise the towers to their full height of 566 feet. Then they build out the concrete viaducts from the shore to the towers.
These projects have been the most difficult because the weather can be extremely tough.
In this part of the world, temperatures will rise and fall by 40 degrees Celsius across the year. This dramatic change leaves engineers facing a big problem. The entire 61,000-ton structure will expand and contract with the changing seasons.
The moving could damage the concrete.
Changes in temperature cause the concrete approach road to grow and move. Expansion and contraction of the concrete could create devastating cracks and eventually bring down the approach road. To prevent this, the team has built the road and tower in separate disconnected sections. And Guttorm has installed 2 ingenious slide bearings between the road and the base of the tower. As the seasons change, this innovation allows the concrete to slide over the tower as the approach road expands and contracts. This will ensure that the concrete structures don't tear themselves apart and should keep the bridge open all year round.
I'm checking the slide bearing. The whole viaduct has moved 1.5 centimeters, but it will shrink and expand depending on the temperature.
With the slide bearings working effectively, the team tackle their next colossal challenge: installing the bridge's mammoth 5,774-foot-long main cables.
The cables is the one that will carry the weight of the bridge deck and the traffic load. So this is a very important part of the bridge.
But making cables that are strong enough to suspend over 12,000 tons of weight is no simple task. Each main cable is made up of 40 strands. Each strand contains 127 individual steel wires and weighs around 50 tons. Workers use winches and pulleys to drag each strand one by one up and over the tall towers.
This is actually quite a milestone for the bridge when they start pulling these cables, so we are very excited. In a good day, they can pull up to 3 strands, but the average is 1 strand each day.
But with less than half of the main strands in place, the Arctic weather begins to wreak havoc. Deadly winds batter the wires.
Wires are moving and dancing around. The west cable was actually blown over to the east cable and hitting the other cable. So it was a dramatic situation we were in, and actually we're quite scared for the bridge and for the wires that they were damaged.
So the team evacuates the bridge.
I had the feeling that the tower was moving, so then we thought it was best to get down.
The following day, the deadly winds die down, allowing the team to continue to secure and compress together the wire strands to form the bridge's massive main cables. At either end of the bridge, they anchor the cables into the ultra-tough Norwegian mountains to hold them steady.
Mother Nature built our anchor blocks and we used them. We are now in the anchorage hall. This is the very end of the bridge, where the anchorage of the main cable ends in a massive concrete wall.
To make the anchor's base strong enough to hold the bridge, the team has excavated a cavernous chamber over 150 feet down, right into the heart of the mountain. Inside, they've installed a massive 8-foot-thick concrete wall. To connect the bridge into the anchor's base, first they separate out the strands. Then connect them all to the tension cables that run down through drill holes to the wall where they're gripped tight. The wall acts like a giant brace. It uses the mountain itself to hold firm the weight of the bridge.
This concrete wall and the volume of the rock is actually what is holding the bridge.
With the bridge's towers and cables in position, the team face their next big challenge: construct and install its road deck. Suspending a road across this freezing 980-foot deep fjord is fraught with risk. Structural engineer Jamal must design a roadway that can withstand the ferocious Arctic storms.
The biggest challenge in this area is the wind. You have a lot of turbulence, and that's due to all these mountains. So for the bridge deck, you have to design for the wind speed where the bridge get unstable. And as a consequence, the bridge deck can get destroyed.
Strong winds can shake even the toughest suspension bridge to breaking point. This is the Tacoma Narrows Bridge, a 2-lane suspension bridge built in the late 1930s across the Strait of Puget Sound in Washington state. After opening to traffic, the bridge began to shake in an unusual way. Wind passing over the deck caused it to oscillate violently up and down. The slender bridge was not robust enough to take such a battering, and just 4 months after opening, it collapsed.
With the narrow deck, you're working on the edge of aerodynamic stability.
Like the Tacoma Narrows crossing, Jamal's bridge is slender, built to carry just 2 lanes of traffic. But this super skinny design makes the bridge extra susceptible to strong winds.
The wind will create some curls, and you can have the bridge oscillating up and down.
As the wind gusts over a bridge from one side, it travels above and below the road deck. A change in air pressure forces the wind to curl backwards in the other direction as it clears the opposite edge of the deck. This process is called vortex shedding. These wind curls, or vortices, begin to move the deck up and down. They can cause the bridge to oscillate and twist violently. To prevent this, Jamal is designing the edge of the deck on his bridge to have a special aerodynamic shape. It smooths the flow of wind and reduces the vortices. His design should help this bridge remain steady when hit by the strongest gusts.
So one way to mitigate that is to limit this angle to below 16 degrees. Then you can avoid any vortex shedding phenomena.
The bridge's deck is being built in 30 custom-made sections in this factory in China. Each section is made from around 250 tons of steel and is hollow to cut weight. The completed deck sections are transported 12,000 miles by ship from eastern China to Narvik port in Norway.
The vessels from China have arrived, and this is a big moment for us and also for the local people here.
Steel engineer Kurt Grunstad is anxious to make sure that the deck has survived this epic voyage.
Finally, we have the steel elements in Narvik. We have waiting for them for many, many months now.
Kurt's team need to carefully remove the hefty steel columns used to secure the deck sections onto the ship. This is a high-risk procedure.
Removing of the sea fastening is a very, very big operation. It's a high column and it starts waving and it can hit the section, so we have to do it very, very carefully. Because if they get damaged, then it takes 3 years to make new segments.
Denting or smashing any section of deck could put the entire project back by months.
Every one of the workers are very concentrated, and they do it slowly, slowly.
The giant supports slowly clear the danger zone. Kurt must now check each section for damage from the inside. Any holes or rust could compromise the integrity of the entire bridge.
Now we look in the first part of one of the sections inside, and it's painted and it's cleaned. If the section had been filled with seawater, we can have a lot of rust, and I can see that there is no rust in these sections.
The arrival of the deck marks a major milestone for this project. But there's a problem. Winter is rapidly approaching, when plummeting temperatures and ferocious winds will strike this region. To stay on schedule, the team must install the entire road deck before winter arrives.
If we don't get the bridge deck up by the middle of October, we have a larger risk for high wind speed and bad weather. So we have to work for this to happen before the winter sets in.
The first task, fit the crucial 110 hanger cables that will hold up the segments of road deck. Giant clamps are designed to secure these cables in place. Workers test that each clamp is able to hold around 7,000 tons.
It would be a problem if the cable clamp started to glide. A fatal collapse of the bridge decks could be the result. Hva ser ut med det, eller? 47. Yeah.
Oh, okay.
Great.
With the clamps checked, the team then ship each hanger cable from the shore to the bridge by barge.
We have 110 hangers to install, and we must work fast.
This hanger cable weighs around 4 tons. And it's one of the longest, measuring more than 400 feet. Raising this humongous hanger nearly 550 feet above the freezing water will be no simple task. Yu Wei's team up on the bridge lower a winch line down to Yu Guaiyang's team on the barge.
It's a good weather for install the hanger. No wave, no wind, perfect.
With conditions looking good, they start the big lift.
Okay, we are ready.
We go.
2 meter from you.
Barge captain Oddbjorn Martin Luther keeps a close eye on the weather.
Yesterday there was a lot of wind. Today, tide is coming in, so I have to hold on.
Oddbjorn needs to ensure the barge remains perfectly steady on the water throughout the entire operation.
The most difficult is to keep her in perfect position, so they don't get problems on deck. Got a spot on the pillar here, can keep it in perfect position.
The barge team must make sure that the cable doesn't snag or knot as it uncoils.
We must be careful during the whole process. 听到，听到，听到。打钢铁！
To pin the cable securely into its clamp, they break out a hammer worthy of the Norse god Thor himself. With one final whack, this huge hanger is in position.
Okay, stop.
It's a constant battle to beat the tides and winds to install the remaining hangers before the Arctic storms bite. It takes 2 weeks of intense work to get all 110 hangers into place.
Ah, it's good, very good. We have finished. Good job, good job.
Every hanger is placed. It looks good. And this is a milestone because we are one step closer to getting the bridge deck installed now.
The team only has 7 weeks to install the bridge's 30 deck sections before tempestuous Arctic weather threatens to shut down construction work.
The deck installation is very critical because the uncertainty of the weather is increasing as we approach the winter time.
Before they can install the deck, they must push the bridge's 2 massive main cables apart.
We are under a lot of pressure to shift to 2 main cables.
This is the problem. The width of the road deck measures 61 feet across. But because of the tower's slender A-shaped design, the main cables only sit 10 feet apart as they approach the top. As the cables slope downwards, they would start to obstruct the road. To solve this problem, the engineers plan to shift the giant cables further to be 51 feet apart at the center of the bridge. Their idea is to use a series of giant steel beams fitted with hydraulic jacks. These shifting beams will slowly force the cables apart by 3.9 inches per push. They must repeat this process until the cables are correctly spaced out along the entire length of the span. Site engineer Yu Wei oversees today's crucial operation.
Today is a big day. We have 7 shifting beams and we have 40 people on the site. Now we are ready to shift 2 main cables.
With beams and teams in place, they start the big push.
Hello.
It takes around 30 tons of hydraulic force for the jacks to slowly push the two 2,000-ton cables apart, inch by inch. Once each jack is fully extended, the team must retract and reset them, ready to push again. It takes 6 hours to push the cables 13 feet apart. But just as they hit their stride, the wind picks up.
Hello, Kurt. I'm calling from site. Do you have any control on the weather forecast?
I can see on my screen that the wind speed will rise up to the limit that they can work on catwalk.
I see. So they need to make the decision to stop?
Yeah.
Okay, so the information we got was that the wind speed is rising. So we will stop the shifting and wait till the wind settles.
The increasing wind forces the team to down tools and abandon today's operation.
It is very important to finish tomorrow, or we will run out of time.
With the team waiting to install the deck, this delay couldn't have hit at a worse time. They have no option but to return to base camp, where head chef Yang Geli is preparing this evening's meal for the Chinese members of the workforce.
这道汤在中国是很流行的，所有的人都喜欢。
Geli was specially flown in to give the 50 Chinese workers an authentic taste of home during the construction and keep morale high.
We have our chefs and we do the Chinese food here. For any person, they eat the same food for so many years, maybe 40 years or 50 years. To change the foreign food for just one year is impossible, I think.
On the menu tonight, egg and tomato soup followed by beef with rice.
It's very good for our workers. If the food is not okay, I think no one will work.
After a busy day, the team finish up with a game of pool to recharge ahead of another day's work. The next day, there's a break in the strong winds. The team must seize this chance to finish jacking the bridge's main cables apart.
Now we have 54 meters, but we have 11 meters left. Oh. We have just 10 centimeters left.
Yu Wei and his team work tirelessly through the day to haul the cables apart.
Okay. Now we have finished. The 2 main cables is 15 meters apart. 好嘞，好嘞，我们都丢完了哈，大家可以下班了。
Success. Against all the odds, the weather holds out. Now the most daunting work can begin, installing the bridge's road deck.
We have been waiting for this for 4 years. And tomorrow it's going to be lifted. It's amazing.
Lifting the sections of road deck into place will be the team's toughest challenge to date. Once they start, they must not stop until at least 3 sections are fixed into position.
It's extremely important for us to have the 3 deck segments on place, because when the 3 segments are on place, it's stable. And the forecast says it's going to be okay weather for the 3 next days. So we have this little time window with good weather, and we cannot have anything happen that delays this process.
To lift each of the 250-ton sections into place, they need to use this mammoth floating crane. It's called the Oogland. The Oogland is the biggest floating crane in the country. Its giant lifting arm soars nearly 400 feet high and has a lifting capacity of nearly 800 tons. But making sure they lift each piece of road deck into the right spot will take careful coordination as the vessels shift around on the water.
We have the ship with the bridge deck, we have the floating crane. So it's essential that both these boats are anchored correctly and safe.
This is the plan. The ship carrying the deck will connect to 4 anchor points in the water and 2 winches mounted below the towers. These winches will pull the boat back and forth into the correct position for each lift. The team also plan to connect the floating crane to both the anchor points and the ship carrying the deck. This will ensure that the 2 vessels move in unison in the water. The crane will then lift up each section to the cables. Then the team will connect them to their mountings. They must repeat this process, joining at least 3 sections together within the razor-thin window of calm weather, or the deck won't be stable enough to withstand the battering from the incoming storm. But doing this won't be easy.
The platform is ready to lower the...
easier.
Yeah. The first lifting is a challenge because if the segments start waving, it can hit the catwalk. We have a lot of people here working, so they need to be very, very careful when lifting.
The first massive deck section lifts off.
Oh, it's coming closer and closer.
The crane slowly raises the first 250-ton section to its mounts. The team keep a close eye on the weather. A sudden gust now could blow the giant crane into the main cables and cause catastrophic damage.
So far, it's looked good.
They line up the deck, insert the locking pins. Now it's hammer time again. It takes over 3 hours to lock the first section into place.
Perfect. Now pins are installed, so now they will disconnect crane and the lifting gear. I feel very, very great.
The first section of deck suspended from the bridge marks a major milestone for the team. But they're rapidly losing light.
One segment now and 29 to go now.
It's taken most of the day to position the first section of bridge deck. They can't afford any delays if they're going to beat the high winds. After 72 hours of exhausting work, they make their deadline.
It looks very good. We're gonna be safe.
With a hefty 750 tons of steel deck installed, the bridge is now robust enough to survive a storm. Over the next 3 weeks, the team ramp up the pace. They lift, haul, and secure the next 22 segments into place one by one.
Everything goes smoothly. I think it's okay.
But with just 18 days until the winter weather is due to set in, progress grinds to a halt. Strong winds and fast tides make it too dangerous to lift the last deck sections into place. It's a huge setback.
It is really frustrating, but hey, we're building the longest suspension bridge ever attempted in the Arctic, so you wouldn't want to be caught with 280 metric ton on the hook and then the wind would rise, you know, that would be a disaster.
The delays don't only cost precious time, they also threaten to push this £332 million project over budget.
The tugs, the anchor setup costs around 100,000 euros a day, so we're anxious to get started and finish the installation as fast as possible.
With the strong Nordic winds raging through the mountains, the team has no option but to down tools and wait for calmer weather. Finally, after an anxious few days, the winds die down. Dagrun's team gear up to complete the last critical milestone.
Right now we are waiting for the floating crane to come into position to put up the last element. This is really exciting.
This is the moment they've all been working towards for the past 4 years. The floating crane carries the final deck section to the bridge. With the wind at bay, they seize their chance to start the final lift. The entire project hinges on this moment.
I think it's gonna fit.
But it will be a tight squeeze maneuvering this 131-foot-long piece into the gap. One wrong move could put the deck section onto a collision course with the rest of the bridge. The crane slowly raises the deck above the roadway. This gives the team some slack to connect the hanger cables.
When they release the crane, then it will come down. So this, I don't think we will have this difference in the height.
With the hangers connected, the crane slowly lowers the final segment down to allow the hangers to take the full weight. The moment of truth. Will the two sides of the bridge line up? with some gentle persuasion, the bridge finally joins together. For Dagron, Kurt and the team, it's a huge relief and the end of an epic journey.
We are finished! Yeah!
Today we can start walking from the north side of the bridge and go over to the south side. We have looking forward to this moment for a long time now.
To mark this momentous achievement, Dagron and her team make the very first crossing over the new bridge to celebrate with the rest of the crew.
First trip on the Hålogaland Bridge. I really want to thank every one of you who has participated with all your skills. Today we celebrate the Norwegian way with coffee and cake. So congratulations to all of us for this milestone. Thank you. Thank you.
The completion of the deck marks a key milestone in this ambitious £332 million project. All the major construction work is now complete. The team has poured 32,000 cubic meters of concrete, secured over 11,000 miles of wire into the mountains, and installed 7,000 tons of steel road deck.
This will be a landmark. So I can tell all my friends that I have been building this bridge. This will be a memory for the rest of my life.
It's quite a challenge to build bridges. It's quite special. So when I go back to sit in the office, I will miss these days.
Over the coming months, the team will wrap the cables to protect them from the elements and top the steel deck off with the all-important tarmac roadway to finally complete the bridge.
When we have this new road, it will be, I'm quite sure, saving lives.
For the residents of Narvik, today signals a huge step towards a more prosperous future for the area.
This bridge means that we can develop our city. This connection goes directly to Europe, and I'm very excited to see this bridge opened.
The brand new Hålogaland Bridge will cut journey times to neighboring cities and provide a safer passage north for the residents, ensuring Narvik thrives for generations to come.